working on my end. Okay, so this is the bonus lab for EECS 281. We're just going to go over a bunch of high-level concepts that you're probably not going to learn in any other class here at Michigan, but are, I think, super fun and useful for advanced C++ programming. And super stoked to see so many of you here. Just as a disclaimer, this is going to be a long talk. So if you want to tune out or just watch the recording, or if you already know a section of things, I won't be offended if you leave. But it should be a lot of fun. I've thrown in some breaks, and we have some like fun trivia and live demos and stuff like that. So hopefully it won't be too much of a drag. Okay, so here's the agenda. Move semantics, smart pointers and RAII. We're going to talk about lambdas, the singleton pattern, tries, polymorphism, and how that actually gets implemented in C++. Very small section on variadic templates, and then some additional C++ 17 features, namely structured bindings. And then we can do some open Q&A, and if you guys have any other questions, we can take it wherever you want. So some intro before we get started. This stuff is really hard, and I'm just a student teaching it, and I only learned this stuff semi-recently, the last 4 years of my college experience. So yeah, there are entire courses on some of these topics. So please ask questions if you feel lost. I will do my best to explain everything, and we're all here to learn. So if you don't understand something, you are certainly not alone. It definitely took me a while to get these things right the first time I was learning them. So, yep, back and forth required. Embrace it. Don't be silent if you're feeling lost. If you want to learn something, that's why we're all here. So be sure to ask questions. And of course, disclaimer, it's hard, but it's also fun. Okay, so this is a little thing that I added pretty recently. If the slide has a yellow background like this one, then it's an extra slide. So I don't find the content particularly useful, but it's cool to know, or I find it very difficult and I'm not sure that many people are going to get it on the first try. So if you see a yellow background slide, this is an opportunity to ask more questions or to let it go if you don't think it's something that's going to be useful for you. And I'll try to explain every time I get to something that I'm not sure is super useful. I'll try to explain, you know, this is something that if you don't understand, feel free to just let it go. Okay, so let's get to move semantics. And this is a beefy one to start us off. Okay, so does everybody remember from EECS 280 the rule of 3? And can I get some confirmation or some no's in chat? Because I legitimately do not remember if that is a big topic in 280. Okay, it's a big topic. Cool, good to know. But I guess for anybody that doesn't remember or who wasn't here at Michigan or just transferred or something like that, if you need to define one of the following for a class, the rule of 3 states that you should probably define them all. And those 3 things are the copy constructor, the copy assignment operator, and the destructor. And the example that is used in EECS 280 is if you're going to manage some dynamic memory with some class. And the classic example is to write a vector class, which manages a fixed size array under the hood, and then it will grow that array as needed. And if you need to do something like copy that vector with a constructor and assignment operator, you need to be sure to give the other object control of a deep copy of your data, not just a shallow copy. And then in the destructor, you need to be sure to clean up your resource. So with the rule of 3, we can kind of start to see some areas where it needs to be fixed. And let me copy and paste this link in the chat. So if you want to follow along with this code example, head on over there and hit the blue fork button, and I will be doing it on screen if you would rather just watch along. Yikes. Okay. This is super small. Wow, this is terrible. Okay, let me just pull it up on my ID, but you guys can do that. Okay, you guys can still see my whole screen, right? You can see VS Code right now. I get a confirmation. Sweet. Okay, so a brief demo with a vector class, much like the one that I was just outlining. So let's just look at this code really quick. And you guys follow along in that replit if you want. You can hit the run button and do make copy, I think, to make the executable. Anyways, there's this myInt vector class that I've created. It has private data pointer, which just points to some fixed size array under the hood. It's got a capacity, it's got a size, and it's got some ID field, which is just used for printing. We've got a constructor that prints out when you first default constructed an object. We've got a destructor, which prints out when you've destructed and deletes the data. And then, basic copy constructor, which does a deep copy assignment operator, which just does the copy swap method. And then we have a swap function. So this is pretty straightforward. It's going to behave just like a normal vector. And this is really just for demo's sake. So can somebody tell me, I guess let's just go with this first. So I just made this copy. We're going to run this code, and I'll just show you what gets printed. So before we get too far, let me make this bigger. Just have that thought. So in main, what we do is we're constructing this vector. Is there a question?
Sorry.
No, yeah, go ahead. Oh, if you just had your mic on, no worries about that. So
yeah, sorry about that.
That's totally fine. So we're constructing this first vector. Vector constructing 1 gets printed. And then when I push back all this data, something may happen. But really, we're just storing the data. And then I'm printing the data. And we can see we're printing vector with the ID 1. It's got size 5, capacity 8, blah, blah, blah. It's got all this data, just like we would expect. And then we destruct 1. Now let's take a look at our second example here. And this should be pretty basic for everybody so far. Whoops, did I hit save? Nope. So second example, we've got similar stuff here. We've got a copy constructed vector 2 from vector 1. So we expect this to do a deep copy. And that's demonstrated here when we push back 6 into vector 2, but the values contained in vector 1 don't change. So print out the starting data from vector 1 up here, and we get 1, 2, 3, 4, 5. Then we copy construct 2 from 1. Then we're pushing back 6 only into vector 2. Then we print the data from myInt vector 1 just to show that we did not add that 6 to vector 1. And this should be pretty straightforward. This is just the idea of a deep copy. And again, just getting back to the rule of 3, this is just some examples for that. And it will lead into some justification for why we need move semantics. So let's look at one final example here before we get into a little bit of a participation. And we've got all of our output from before. But this right here, we're going to default construct our third vector. Then we're going to use our copy assignment operator instead of our copy constructor. And again, we're going to print it to see that we got 1, 2, 3, 4, 5. Oh, wow. I haven't done this in a while. Let's see what's going on here. So we're copy assigning 3 from 1, which is this line here. Copy constructing 4 from 1, and then destructing 4. Guess I should have ran this example one more time before we started. I'm not quite sure what's going on there, but might be because of the compiler flags I'm using. Either way, let's take a look at this line of code right here. This is the real kicker. We're going to see some inefficiencies here. Can somebody take a guess as to what this code will print out? And I will scroll up really quick to this create big vector function. So we have a vector that will have no data in it, and we're going to copy assign it from the result of this create big vector. And inside create big vector, it is just going to create a local vector, push back 10 things into it, and then return the vector. So does anybody have an idea of what kinds of constructors will be called in what order based on this line of code? And this is totally fine if not, because I'm kind of dropping this on you. That is totally fine. Default and assignment. That is a great guess. I agree. I think we're going to get a default, and then we're going to get a copy assignment. I think we're also going to get something that happens in this function too. It looks to me like we're making one vector here and we're making one vector here. So a default constructor, then a copy constructor for when we return by value. Yep, that sounds very similar to what Pranavi said. I agree, those are both good guesses. So let's just take a look at what happens. Okay, so, whoops, did I not save it? There we go. Okay, so here's what happens. Constructing one, and this is vector one up here. So the first thing we do is, whoops, that's totally a lie. This is vector one right here. So we construct one default, like everybody guessed, which was correct. Then we are going to copy construct two from one. Now, where is this line of code coming from? And man, I really should have ran this with a little bit more preparation, because now I need to relearn. So this will be an interactive activity then. The equals operator, that is the guess here. We think that this line right here is doing the copy construction. What do you think about that for a bit?
Yes, it is.
I think you're right as well. This is pretty funny that I'm not as prepared as I should be here.
Though. It's just syntax for copy construction.
Yes, but I'm using the no-allied constructors flag here to prove this demo, and that's what's throwing me off here too, because yes, this would normally just be a copy constructor, but instead we have this third vector somehow. Yes, okay, so here's what's happening. Sorry, I'm finally up to speed. So we have this vector one. This is vector one, and this is just a demo here, so don't take this too seriously, but we have a vector one. It's temporary to this function. As soon as we return it from this function, it's going to destruct. But before we do that, we're creating this temporary vector over here. So the result of create big vector is just going to exist kind of in line right here as a temporary value before it is then assigned to this default constructed vector. So what happens is we're constructing this first vector, one. It gets created, it gets returned from this function. We are copy constructing this temporary vector 2 here that we don't have a name for even. So that's what's happening here. We're copy constructing 2 from 1. This thing right here is a vector. Then we destruct 1 when we return from this function because we no longer need it. We copy constructed this value already out of it. Then we copy construct vector 3 from 2, which is this is vector 3 obtaining the value from that temporary returned vector. Then 2, because it was just a temporary vector and we don't need it after this line, gets destructed. And we can finally print the data from vector 3. Okay, and this example, and some of you who know a little bit more about where I'm going with this are probably going to be annoyed that I use this example, but I'm using this example to show that there are some inefficiencies in certain situations, specifically with regard to vectors that we know are temporary. Like this vector here, the return result of create big vector. We know it's temporary. We know it's not going to use its data after the expression on the right-hand side of this equals operator finishes. So the idea of move semantics is that if we see a temporary vector or a vector that isn't going to need its data anymore, we can simply steal its data and not really worry about the consequences. So I will give you a brief example where we don't elide the constructors there. So previously I was using a flag which told the compiler to make every call to every constructor without trying to make optimizations. But if you were to compile your code normally, you would just get this result. You construct vector 1 and you print all of the data in it. So this vector here never really gets created. The compiler does something called return value optimization, where it sees that this vector is being constructed from the result of a temporary variable, and it just decides to create this vector in place here to begin with. that is kind of a difficult topic to understand the first time around, and I have some slides on it. And this is just an intro example before we get going. Question from the chat, what does elide mean? Elide just means to skip. So you can see here that only one vector was constructed, and really there is at least one more vector that should have been constructed. And because I told, in the first example, because I told the constructor to not elide, to not skip these constructors, it actually ran all of the code as we would expect. But because I allowed it to elide these constructors here, we didn't get this temporary vector construction. Is the compiler basically inlining to minimize calling constructors? Yeah, you can think of it that way for sure. You can think of it as, I guess, something like this, where my vec equals, you know, you can think of it as something like that. Yeah, where it basically knows that it's getting the result of some other vector, and it just decides to create it in place or inline the code anyways. So anyways, this is an example mainly to show you that there are some scenarios in which we would like to steal another vector or another object's data without needing to make a deep copy. So normally in this example, we would need to make a deep copy because this other value might need its data later, and we don't want to modify it. But because we know that this value here isn't going to need its data anymore, we can steal it for free. So we can basically do a shallow copy and get away from doing that O of n work that we really don't need to do. Okay, I'm gonna hop back over to the slides because that's really just the first example here, and it's really just an intro to why we need this stuff. Okay, so the rule of three, we have a tricky situation here. The moral of the story is if we know that the other object won't be using its data anymore, we can just steal it. This is just what we were talking about, and we have no way of doing this with the functions outlined by the rule of three. There is that return value optimization idea that we discussed briefly, but it does not handle every situation. It just handles the specific situation that I talked about there. And the kicker is that the stealing is often much faster than doing a deep copy. In many cases, you can think of it as just like making a shallow copy instead of a deep one. So yeah, that's quick. We'll get back into an example which has move semantics in a second. So this is what move semantics are. You can think of moving data as simply stealing it. And I see some good conversation in the chat. Is move semantics an alternative to copy swap? And a student says, nope, it achieves something different. Moving transfers ownership without copying. I definitely agree with that. It just transfers the ownership of an object. So no copies are made. It just takes the underlying data, and now a new name is referring to that data. So to understand a little more deeply what is going on here, another question from the chat. Okay, so you can't replace copy swap in code with move semantics. Correct. Yep, I agree with that. We will get to an example where I think everyone's questions will be more answered. That was just an intro example there. Anyways, talking about move semantics, we unfortunately need to get into some nitty-gritty first. So L values and R values are two ideas we need to cover. Every programming language has this distinction between the actual value that a variable holds and the name that is used to refer to that value. So in this example here, this screenshot from my VS Code, this S we can think of as a handle on the value itself, and test is that actual value. So there is some data that this string S is referring to, and S is just a name that refers to it. S is just a way to get to the data that it holds, but S is not the actual data. And you can think of this like if you were to do cout arrow arrow S, the data that would get printed is test. You know, the S isn't going to get printed because S isn't data. S is just a handle on what the data actually is. So yeah, I'm going to skip that last bullet point because I think this next slide is a lot better. So this rough definition for an L value is something that can be on the left-hand side of an assignment. So this is the name in our previous example. You can think of it as a location value, as it only represents the location of some data. Variables are L values, and again, these are names that refer to data. They are not the data themselves. And on the other hand, rough definition of an R value, it's something that cannot be on the LHS of an assignment, so it can't be on the left-hand side. You can't assign something to, for example, the string literal test. You can't do, quotation mark test, quotation mark equals 5. Like, you can't put some data into a string literal or an int or an R value. And a good rule of thumb is that these are read-only values, and temporary unnamed variables are also R values. So this is super confusing. I think the best way to learn this is with some examples. So let's just look at some examples. And here's our rough definitions here. Can somebody tell me on this first slide, on this first line of code here, what an R value might be and what an L value might be here? And don't be afraid if this isn't making much sense. I promise it will make a lot more sense after these examples. L value, S1. I agree. S1 is an L value because it is a name that refers to some value. It's a location value. You can think of it as referring to the location of the string literal apple. Totally agree with that. One interesting example of L values and R values is that plus plus I returns an L value and I plus plus returns an R value, but both operators take in an L value. Yes, that's a great point from chat, and you can see that I am going to touch on that a little bit later down. Another student from chat said S1 is the L value and Apple is the R value. Yep, totally agree. So Apple, again, is a read-only value. We can't assign something to the string literal apple, but we can store that data in an L value. We can give it a location. Yeah, so I think the rest of these things from chat look good. One question from a student, can you say 2 equals 2? And I think what you mean is, whoops, spoilers. I think what you mean is, can you do something like this? And the answer is no. This is kind of what the idea of an R value is getting at, is that this right here isn't a name. It doesn't refer to some location, so we can't store something in it. This is an R value because it's a int literal. It's just a number. It's not a name. It's not a variable. So we can't put something in it. And this is kind of the same idea with our earlier example. So we already know that string literals like test are R values. And again, we can't store, we can't store apples into it. This doesn't refer to some memory location, so we can't put something in it. It is just data. So let's hop back over there. Okay, so next line, it's very similar to the first line. We've got, another question from chat actually. Is string an L value? No, so in programming languages, the types and the names of types aren't data and they don't refer to locations. They're just things used by the compiler to basically check your work. And if you work in other programming languages, you'll see that they actually, a lot of them don't actually have type annotations, or they aren't strongly typed at all. Like Python, for example, you can make variables of any type and you can change them on the fly. And under the hood, this is kind of how C++ is, but we have this syntactic sugar of strongly enforcing that your types are correct. So the compiler will do some work before you actually run the program to enforce that you're using these types correctly. But the idea of a type doesn't really exist at runtime. Everything's just data. So no, type names are not L values or R values. They're separate things. Okay, so yep, so S1's an L value, S2's an L value, S3's an L value, and then apple, banana, and orange, the string literals, are all R values. So this line right here, does anybody want to give a shot? What do we think? Are there any L values and R values on this line here? And people can just shout out the rest of them. Yep, vec1 is an L value. I agree. Again, my int vector is just a type, so it doesn't really count. Yeah, and people go ahead, shout out for the rest of them. We got any guesses for these? Already saw a student said, notice that S1 is not an L value until it's used in S3 equals S1 plus S2. Declarations are not expressions. You might need to unmute and explain that a little more if you want to, Brian. I'm not quite sure I understand. I'm pretty sure, at least from, I guess, unless you're saying that until a value is used, it doesn't really exist.
Well, no, it's not until it's used. Are you able to hear me okay?
Yep, I can hear you.
Okay. It says not until it's used, it doesn't really exist. It's just the first line we declare and initialize string S1 equals apple. There's S1 is not used in an L expression. Right? So I guess technically S1 is an L value because it's the name of something, but it's not used in an L value expression, which is really what we mean here. We're talking about L value and R value expressions. But when it's used later on, S3 equals S1 plus S2, then it's an L value.
Yeah.
And it's
Okay.
an L value expression even.
Yeah, I see what you mean. Yep, I agree. I think that's getting into maybe more of the nitty-gritty detail than even I understand, but yep, I agree with that. Declarations are not expressions. Okay, so let's keep going down the list then. So this line right here, x equals 3, y equals 4. This isn't much different. Super simple. X is an L value, y is an L value, 3 is an R value, 4 is an R value. This line right here is pretty interesting. Let me just show the table actually with the answers. So like we talked about earlier, this right-hand side of the expression, of this assignment here, excuse me, the expression S1 plus L2, S1 plus S2, what's going to happen is this is going to use the string plus operator to combine these two strings into a temporary string over here, and then it's going to assign that temporary string into S3. And there could be some optimization that goes on under the hood that compilers do to get around this, but fundamentally this temporary expression, so S1 plus S2 is going to make a temporary variable and then assign the temporary variable into S3. So this is a little bit tricky, but S1 plus S2 is an R value. That kind of idea of S1 plus S2 is an R value. And that's just because, you know, you couldn't do something like S1 plus S2, you know, and then assign some value into it, right? It's just a read-only value. It's a temporary unnamed variable over here, which is our definition of an R value. And then some people talked about in chat, these next two examples, these are pretty tricky. Y equals X plus plus and Y equals plus plus X. You can see here that Y in both cases is an L value, but X plus plus is an R value and plus plus X is an L value. So let me just show you an example explicitly of how this works. So let's do int y equals 0. Geez. Let's do int x equals 1. And then if we do y equals plus plus x, this is all fair and good. And y equals x plus plus, this is all fair and good. These will both compile and run. All right, so compile and run, no errors there. But we can do plus 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 x too. Yes, that is true. But what will happen if we try to do these two? So remember that an R value and an L value are denoted by what can appear on the left-hand side of an assignment and what cannot appear on the left-hand side of an assignment. And we can see that plus plus x can appear on the left-hand side of an assignment, but x plus plus cannot. And you can see that the error that it gives you, and I think this is really neat because you don't really see these things ever, but they are actually real terms. The L value is required as the left operand of an assignment. And it's complaining that x plus plus is not an L value. It's saying you're trying to assign to something that can't be assigned to. It's not an L value. And this is because the way that this works under the hood is plus plus x. This is super bonus data. If this was on a slide, it would be a yellow slide. But the way that the prefix increment operator works, so when you put the plus before the variable, what it does is it increments the variable and then it returns you the reference to the new incremented variable. So you can think of it as, you know, if you have some, I don't know, int R10 or something like that. If you want to do I equals 0, int I equals 0, and then you want to like do R at I plus plus, right? So what's going to happen here is we're going to get, in this case, we are going to get the value at R of 0. So this will give us the value of R of 0, then increment I. That's what this is going to do, as opposed to this line of code, which is going to get us the value at R of 1. If we assume this line of code doesn't exist, well, it's going to increment I, then get R at I. So that's how that works. And the way that this works under the hood is, in this case, we increment the value and then we return the value itself. And in this case, what's happening is we increment a copy of the value and then we return the old value, or we increment the value and then we return what the old value was. So really, we can think of this as incrementing the actual thing itself. So we're updating the location of the actual value with a new value, and we're returning a temporary value, which is the, you know, the int which used to be x, so the unincremented version. So that is a super not important thing to know, but pretty interesting nonetheless. Okay, so that covers those two examples. The prefix operator will increment it and return the actual value itself. So it will return the variable which refers to the value itself, L value, which the postfix increment operator will not do. And then in a much more simple example, you can see that x plus 1, this is clearly a temporary value. So if you wanted to assign something to x plus 1, you couldn't do that. It's just an R value. And of course, the return value from a function call, even if it's a constructor, that's going to be a temporary variable. So, you know, you can't assign something to the result of a function call. So R value. Okay, and just real quick before we get into any of those questions, the key pattern to notice is that none of these R values need their data. They're all temporary objects. And thus, R values are prime candidates for move semantics because we can steal their data without the worry that they will use it. So let me take a look at some questions from the chat. Oh, we've got some great theoretical questions. So yeah, S1 and S2 are not, sorry, S1 is an L value. S2 is an L value because they refer to the location of some data, right? They refer to the location of banana and the location of orange respectively. But the expression S1 plus S2 is an R value. So yes, okay, there you go. So how many gets it? Great. Cool. And then yeah, some more theoretical, how many times can you increment X in a weird way in one line of code in the chat? Okay, so now that we have that super ugly background, let's get to the rule of 5, which is the new rule of 3 and what they should teach in 280 if they had a little more time. So with the introduction of move semantics in C++11, we should now define all of these things if we need to define any one of them. And these two new things are a move constructor and a move assignment operator. So let's get into another example, which is going to be much more, it's going to make a lot more sense. So let me put this in the chat if somebody wants to hop on over there and take a look themselves. Oh, I forgot, I'm just going to go to move. Okay. Oops. So we have our same myIntVector class. And the only difference here is that we're going to have two new functions. We're going to have that move constructor, and we're going to have that move assignment operator. So just as a brief recap on the copy swap method, because the copy swap method is important to move semantics, you can implement move semantics without the copy swap method, but it is very easy to just reuse the copy swap idiom to implement move semantics. So this is our copy assignment operator. This is nothing new. Say we have some swap function, which given the data of our internal class, it just swaps, it does a shallow swap of all of the member variables. And we're not swapping the ID field here. That's just because I wanted the printing to come out nice. So we have our swap, which does a shallow swap. That's all we need to know. And we do copy assignment by making a temporary copy constructed class object from the other one. So we're doing a deep copy on this line, and then we're just doing a shallow swap with this current object and the temporary one we just constructed. So yeah, the idea there is we are making a deep copy into this temporary variable, and then we're just taking the temporary variable's data and letting the other one destruct with our lack of data, I guess, or whatever we previously had. So we're giving this temporary variable whatever we previously had, and we're letting the temporary variable destruct at the end of this function. So that's the basic of copy swap. You make something and then you swap with it, and then you basically get that new data. So move constructor. This is going to be the signature of a move constructor. Why static swap? A question from the chat. Wait, not static. I'm not quite sure. Oh, yeah. That's a good call. This should be static. Yep, good call from the chat. Yeah, totally good call. Anyways, move constructor. First thing to note, this is a weird function type here, or parameter type. This looks like it's a reference of some kind, but we've also got two ampersands, which I'm sure you've never seen before, except for in like, you know, Boolean expressions, true and false or something like that. But this double ampersand in C++ refers to an R value reference. So remember, R values, we already know, they refer to some temporary unnamed variables. They're read-only. They're prime candidates for stealing. And the compiler is able to recognize when these types of objects exist. And we can take advantage of that by writing overloaded functions, which will only be called when the compiler recognizes that the argument is a prime candidate for stealing. So just a brief recap of function overloading, because that was an important thing I just said, is we've got two functions with the same name here, and they both take one argument. So we've got this myint vector function and this myint vector function here. They're both named the same thing, and they both take one argument, which is of type myint vector. So what the compiler does when it sees two functions with the same name, and I'm saying function, but constructors are just functions. There's no difference really. And what happens is the compiler is going to choose which one of these signatures matches the parameter most closely. And in our case, this means we get to take advantage of the compiler telling us, the compiler does the work for us by telling us when the object is prime for stealing. So in this case, if this function is called, we can recognize that this we can recognize that this other object can have its data stolen. We can move the data, we can steal it from it. Okay, so what this means, if we already know we can steal something, we're gonna print something here, and then we're just gonna do a shallow swap. That's it. All we do is shallow swap. And if we think about this, it makes sense. We are just taking the other guy's data pointer and we're giving him ours. We're taking his capacity and we're taking his size. And that is all you need to do to steal the data from a vector. So yes, good on me for writing this note. So this up here is very important. Remember, we can do initializer lists and constructors to, I guess, have some stuff happen before the body of the constructor. That's a simplification. But what we're doing here is we're default constructing ourselves. So we are giving our vector default data. And if we go on up to this function, we can see that it's just giving us a size of 0, capacity of 4, and then some just default for array under the hood there. So we're giving ourselves default data, then we are swapping our data with the other vector. So we're essentially stealing the other data's vector and we're giving him our default constructed value. Some questions from the chat. Student says, one difference between a function and a constructor, you can't take the address of a constructor. Yep, sure. What makes this different from how we normally do copy swaps? Yep, so that's a great question. Let's just look at these two functions. So copy constructor, what it's doing is it is doing a deep copy. It is doing this for loop from 0 to size, and it is manually copying the other vector's data. And in this case, we are not doing any of that. If we look at std swap, if we look at our swap function and how it's implemented, we can see we're just doing a shallow copy. So remember, data is just a pointer. We are just taking the address of the pointer. You can think of this as like, I would need to draw a picture to do this nicely in office hours, but we're just doing a shallow copy. There's no O of n loop here. There's no for I equals 0 to I at size. We're just taking the pointer and we're taking the capacity and we're taking the size. So it's a lot faster. And that's kind of what this is getting at. And that's how you can take advantage of move semantics. And then there's this move assignment operator as well, which is very similar to the move constructor, except it returns this object as well. Yeah, I feel like I flew through that. Please ask some questions if you're not following. But until then, I guess let's get into the example. This is, okay, questions from the chat. So this is when we don't need to keep both data structs. Basically, we just need to keep one. Yes, and that is the key example, or that's the key point here, is that this type, remember this double ampersand means R value reference. And from our previous slides, we know that R values are representations of data that are temporary. They don't need their data, so we can take it from them. And the compiler will do all the work for us of making sure that these functions are called when the parameter is a type that is prime for stealing. So yes, the difference here is that we do not need to keep around both of the objects in question. We only need to keep around whatever's being constructed here. This is this object, and the other object does not need its data anymore. So we can let it destruct with any data that we give it. Okay, I'm going to get to this example here. So this is the same exact code as it was last time. Only difference is we now have move constructors. So let's do make move, and let's just take a look at this. So constructing one, this is again, oops, right here. This is again vector number one, constructing two, which is this temporary vector right here. So this is vector number two that gets created. We move construct two from one. So when big vec is returned, it's getting returned to this temporary right-hand side expression. And we're using move semantics because the compiler recognizes that this returned value here isn't needed anymore. So, I mean, if you just think about this logically, this myint vector big vec will not even be accessible after the return of this function. So it doesn't make sense to copy its data. Rather, we can just steal it because clearly big vec will not be referenced after this return line here. So we can steal it. The compiler recognizes that and it calls our move constructor instead of our copy constructor. And then again, because this is a temporary variable, we can move construct our vec3. This is vec3. We can move construct our vec3 from the temporary variable here as well. So that's what happens, and we can get away with doing absolutely no copies in these lines of code. And one more thing to show you, I guess, any questions, please feel free. I will slow down and answer them. But if we remove that allied constructor or that no allied constructors flag, so remember I told the compiler to not make any extra optimizations. I told it to just call all of the constructors that it saw there. And if I tell it that it's allowed to skip the constructors, we can see we just get constructing one and destructing one. And this is the idea of return value optimization. And there will be a slide on this right after we get it back in this demo. But again, this is the idea where there's this temporary vector that we're constructing. We recognize that it's about to be returned, and it's about to be, specifically, it's about to be returned into some other vector. And the compiler just recognizes this and says, you know what, let's just skip making this internal vector to this function. Let's just build the vector in the place where it's going to be returned to. And you can get away with not even calling the move constructor. So that stuff happens automatically, but there are definitely other scenarios in which move semantics are useful. Okay, so question from the chat. Yes, yes, you can make comments in the middle of a line. You can make this style of comment with opening with these two characters and closing with these two characters. You can make it a multi-line comment, but you can also close it in the middle of a line. Not super useful, to be honest, but yep, you can do that. So the compiler auto does this for us for some optimizations. Do we really need to do this ourselves? If so, why? Great question. So return value optimization is a change that compilers are allowed to make. So normally compilers have to abide by some rules, specifically what's outlined in the standard. So I guess an example would be if we look at the changes that the compiler made to our code without us asking them. So the compiler, this is what our code should print if it's calling all the correct functions and calling all of the correct constructors. But what actually gets printed is this. And you can imagine, say we're in X281 and our project is graded based on the output of our code. We can imagine that this might not actually be what we want. We might not want the compiler to, you know, avoid making function calls just because it detects that it's optimal, right? There was a change in the output of our program. Our program changed because the compiler made this optimization. But return value optimization is such a commonly accepted optimization that compilers are explicitly allowed to make this this change. There are other cases, though. Go ahead.
In C++ 17, return value optimization is required in some cases. So if you were to compile this code with C++ 17, you'd only see one move constructor call, not two, even with F-no-allied constructors.
Really? Oh, that's super neat. Yeah. I might have to try that after this. But yeah, anyways, return value optimization, it happens. That's not a controversial thing. This is one example where I guess you can think of move semantics as just being mandatory. It's already implemented by the compiler. And the question from the student, which is really, do we really need to do this ourselves? Yes. So there are plenty of examples of situations where the compiler will not be able to automatically recognize and make this optimization for you. So return value optimization, yes, the compiler will do the stealing for you. It will make the optimization for you. You don't need to do a thing. There are plenty of opportunities, though, for you to take advantage of this in your own code. For example, project 3. Does everybody remember the set intersection code, where we had to create some vector and then continually set intersection it with some temporary vector in a for loop? Yeah, exactly. Okay, yeah. So Brian's getting onto something there. There is in that code, it looks something like, I don't know, for blah vector int, I don't know, a something something, and you had a vector up here, vector int, I don't know, fixed. You had something like this, and then what you wanted to do was set intersection fixed a, and then like assign it to fixed or something. I don't know. The bottom line is there are situations where the compiler will not recognize that something is a temporary variable, but you as the programmer know that you can steal its data. So taking advantage of this is just further optimizations you can make to your code. On top of that, there is some data that is just expensive to copy, right? So, or maybe not even copyable at all. So this example right here, it's just a simple vector class. It's not like super performance. I don't know. It's not super necessary to be high performant. But you can think of some examples where you might not be able to make a copy at all. Like maybe some, I don't know, student record, some medical record where you don't want the data to be copied. It would be important to be able to move that data around without having two representations of the same object. This is a super abstract, I guess, topic without going into concrete examples. And I did pick an easy example on purpose, but I do promise that move semantics are prevalent and they are useful. So let me just print this, print the result of this. We've got what we expected from that first part. We already talked about this, and then we print the data, and we can just see that it has 0 through 10. So we successfully stole this temporary vectors data. And I'm actually not going to do this. If you want to, at home in the replit, comment out this part and see what he compiled, or see what gets printed. And a good point from Brian Rago here. Let me just yoink this. Whoops. Let's try with the oh, would you look at that? Totally right. Okay, so yeah, the RVO is required by compilers in C++17, and we can see that because even with F21 constructors on here, we've got, I guess there are 3 vectors and there are 2 move constructor calls, but if we specify C++17, there's only 1 move constructor called. And that's because this optimization of creating this temporary vector in place, whoops, creating this local vector in place here, geez, just trying to highlight this, is required. Okay, so let's hop back over to the code after a long intermission there. Whoops. Oh, yeah. So it's been a while. Feel free to take a short break if your brain is fried. But here's a couple of trivia things. I'm stealing this from EX481, where there is trivia in class because nobody can pay attention for an hour and a half straight, much less for 3 hours. So can anybody tell me in the chat, and feel free to take a guess if you don't know, which of these titles is the highest selling video game of all time? And this is just highest number of software units sold independent of platform. So Tetris, I believe, counts every iteration of the base game Tetris. Does Fortnite count if it's free? Yes, it does. Free games do count. So we have guess, Minecraft, Tetris, Minecraft, Tetris, Minecraft, Tetris, Minecraft, Tetris. Wow, you guys are going back and forth. Okay, so it's between Minecraft and Tetris. Somebody guessed Wii Sports, which I love that guess because I actually thought it was Wii Sports when I was making this slide, but I'm actually incorrect. Unfortunately, it is not Wii Sports. GTA 5, we got GTA 5 in there too. I think GTA 5 was at one point, but unfortunately it's not. Anyways, now that everybody's got their guesses in, feel free to keep track of your points too. Answer is Minecraft, and it's actually Minecraft by a lot. Let's look at the list here. I'm pretty sure there's a Wikipedia. Yeah, there you go. And these were the top 5 except for Fortnite, which is not even close. I just threw that one in there because I thought that would get somebody maybe. But look at that. Isn't that ridiculous? It's like, I don't know, one day it'll get to twice as many sales as GTA 5. Pretty neat. Yeah, and Tetris counts every platform it's ever been released on, including mobile, which I just think is hilarious. Okay. Trivia number 2. this is, I think, a little bit of a harder one. So, Eliud Kipchoge. The question is basically, who is this person and what is he known for? On October 12th, 2019, Eliud Kipchoge was the first human to ever do what? And some hints: he was born on November 5th, 1984 in Kenya. You guys all know this in the in the chat. He's the winner of 5 Olympic medals. He was repeatedly equated, sorry, this feature was repeatedly equated to the moon landing of this respective field, and it stands alone to this day, although it is sometimes critiqued for having been over-engineered, and a ton of people either remember this moment or are runners or are familiar with Eliud Kipchoge, but this is running the sub 2-hour marathon, which he is the only person to have ever done. Yes, and somebody touching on a little bit of the controversy there. What does that mean? It means that he ran a marathon, so 26.2 miles in under 2 hours, and that has previously never been done by a person before. Yeah, sub just means less than 2 hour. So sub 2 hour marathon means he finished in less than 2 hours, which is, you can see the timer right here was a 1:59:40, so 20 seconds away from hitting 2 hours, but still finished in time. Yeah, and I won't touch on the controversy a ton here, but I can say a little bit. Basically, this was not a race, first of all. It was just him running. It was an event put on by a company, and they set the whole thing up to try to break 2 hours, basically. And all these people in the background, these are not runners. These are his pace team, and they were running in front of him to cut down the headwind. They also picked the date specifically so that, you know, the weather was optimal for like long distance running and like airflow and stuff like that. They picked the track that was like super close to sea level and super flat, and all of this, I think basically like the committee that handles like world records and stuff like that said like, well, you know, for our races, we have everybody racing at the same time, and like, you know, we don't have like perfectly flat tracks, and obviously they don't have, you know, pacing bikes and pacing runners who are running in front of you to cut down your wind. So, you know, this seems a little bit over-engineered, so they didn't count it as a world record, but he's still the only person to have ever done it. So super, super cool. And for some fun facts for anybody who's ever run a shorter distance than this, but never a marathon like me, this was, I think, a 4.5-minute mile for 26.2 miles straight, which is absolutely ridiculous. I cannot imagine that. Anyways, back to the goodies. So rule of 5, we're almost done with move semantics here. Basic refresher: if you need to define one, you probably need to define them all. And yellow slide, first yellow slide, return value optimization. We already talked about this. I'm going to skip this. Yep, and I will update this slide later because I learned something new, that in C++ 17, it is no longer allowed, it is required. Okay, so let's skip over this. One final thing about move semantics: there is a function called std_move. And from CPP reference, here's just the description. Std_move is used to indicate that an object may be moved from, i.e. allowing the efficient transfer of resources from, that an object T may be moved from, allowing an efficient transfer of resources from T to another object. It is exactly equivalent to a static cast to an R-value reference type. So in other words, if you use std_move on an object, you are just telling the compiler to interpret this value, which likely has a name in this context and thus is an L value, but you're telling the compiler in this instance to interpret it as an R value reference. So here's a very quick example. Let's say we have some function foo, which takes in an R value reference, and we say we have some function foo, same name, which takes in a const L value reference. So version A and version B. We have my_vector v constructed with some data. I'm not even sure if this is illegal. I guess it's definitely not legal because I didn't write it for this my_vector class. But question: if we do foo of std_move of v, which version of foo will be called? Anybody have a guess? I'm asking because, yes, A. And that's exactly what std move does. You can think of it as just casting this vector v, and vector v has a name, right? So it's an L value, and specifically this const L value reference version of foo would be called, but because we called std move on it, we told the compiler, hey, interpret this value as an R value reference. So now version A will be called. Then what about this one down here? This is a little bit easier. Yeah, so this one is just going to call version B. So std move isn't a permanent effect. Just like a static cast isn't a permanent effect, it's just going to affect this line here. So when we call foo of v down here, it is going to, I guess, it's going to recognize that this is an L value reference. Again, it's a name. We didn't call std move on it, so we're going to get this L value reference version. And a good question and answer in the chat with how do you write a constructor that allows the syntax for initializer list. Student says with std initializer list, and to be honest, I did not even know that. I would have just wrote a range-based constructor and changed the code to account for that. Anyways, so some problems here though. What if the R value reference version of foo steals the data in V? So remember that we said that when we tell when we denote an object as an R value reference, we are saying basically that its data can be moved or stolen from. And if we call this function, there is a chance, a pretty good chance, I would say, that this foo is going to steal the data, or it's going to modify our data in some way. And the bottom line is that after an object has been moved, you should not rely on the state of it. You should generally, especially if you're calling a function that you didn't write, you should treat the state of your object as undefined after you've moved it. So the bottom line here is this second version of foo, if this was real code, this would be a pretty dangerous function call because we don't know what the first version of foo did to our vector v, and then we're trying to call a version which is basically saying, you know, there is a valid state of data in our vector. So yep, I just said that we have no idea what the internal state of v is at this point in the code, and foo v probably won't do what we expect. Std vector is guaranteed empty after it's moved from, std string is not. Yeah, that's a good piece of info to know. Universal references and std forward. I'm going to very briefly touch on this. This is super not important in my opinion. So let's say we want to write a function that could take in both L values and R value references, but still remember what type they originally were. So there is this thing that allows us to template the type of a value using universal references, then access the underlying value of the type using std forward. So little example right here, let's say we want a function bar that based on the type of the vector passed to it, the type being R value reference or L value reference, it will call the right version of foo inside of it. We can use universal refs and std forward to achieve this. So let's skip ahead. Again, we have our two versions of foo. We have a template type named t. What we do is we have bar take in what's called a universal reference, which is a templated type, which has the R value reference $& syntax. And then it will call foo with std forward of t vec. And this, what it will do is it will forward the true underlying type, whether it be R value reference or const L value reference. It will forward that type to foo, and the right version of foo will be called. So in this case, we have my vector v. We'll call bar of v, and what's going to happen is this std forward foo call will recognize that vec is an L value because we std forward it. So this will call the version B of foo, but this one, which is actually an R value reference passed to bar, will std forward it as an R value reference, and we'll get version A. And this is, in my opinion, super not important. I have never used or seen this in real life, but potentially you'd want to reduce some code duplication here. Yep, that's a little note, not that important. Okay, so this is our last thing on move semantics. And then we will be on to bigger and better things, although move semantics are really cool. So final thing, oops, I guess, again, I'm not doing that, I'm doing this. Let's go to quiz.cpp. Okay, so what I would like everybody to do, oh, this is not visible, painfully not visible. Okay, well, we'll give it a shot. We have our myInt vector class. Yeah, okay, we have our myInt vector class. We have these functions here. This is pretty much what we just showed. I'm going to delete all these spaces so hopefully we can see exactly what's going on here. Yeah, perfect. Okay, everybody take a look at this code real quick and give me a guess of what you think this line of code will print. Any guess is a good guess. I promise I don't bite. Foo with R value reference. So let's find out. So we have bar, and at this point in the code, this myInt vector is definitely an L value. So then we have another guess for foo with const L value reference. So we got both sides of the same coin here. At this point in the code, V is definitely an L value. It has a name, it refers to some location. So if we call bar, let's find bar, we are going to get, and there's only one version of this anyways, the const L value reference version of this function. And then it will call foo. And at this point in the code, even though this is templated, it's still a const L value reference. So foo will be the const L value reference version. And just to show you, foo with const L value reference. Okay, any guesses for this next line? Baz of V. Student guess says the same thing. Well, let's find out. Foo with const L value reference. Great call. So let's trace through exactly what happened there. We have Baz of V, and here we are using a universal reference. This is that last slide there. We have our templated type, and it is taking it in with that double ampersand. So if it's templated and it uses double ampersand, it's called a universal reference, not an R value reference. Super confusing. You don't need to know it. And then we are forwarding the true underlying type of V, which is an L value reference because it has a name. We're forwarding that to foo, so we get const L value reference version. All right, what about backs? Backs of V. Student guess is foo with R value reference. Well, let's give it a shot. Foo with const L value reference again. What happened? Oh no. Okay, and this one's definitely tricky. I didn't expect anyone to get this, but again, this is a universal reference. So we're templating the type and we're taking it in as an R value reference. And just if anybody's confused, if we had this, this would just be an R value reference. So you can't, well, I guess we would need to write the type here. But because it's templated and we have this double ampersand here, it's a universal reference. And what's going on here is because this has a name as a parameter, and it is thus a local variable to this stack frame, right? It has a name. So when we are passing it to foo, we are passing an object with a name which refers to some location in memory, which is an L value. So even though you know, we took it in as a universal reference. Because it has a name, it's still an L value. So when we call foo, we're going to get the const L value reference version of it. And the way that we would need to write this code to access the underlying R value-ness, if it was an R value, would either be to use std move, which would just, like we talked about, whoops, like we talked about before, this right here would just tell the compiler, like, you know, treat this as an R value reference, or we could use std forward as we did above to access the true underlying type. But in this case, that would still be an L value reference. Okay, and what about bay? Finally, surely there are no more tricks. Anybody have a guess for bay? Oof, and here I am cackling maniacally because, believe it or not, this code does not compile. I've tricked you yet again. So, so let's take a look at what happens here. There's an error, cannot bind R value reference of type myint vector R value reference to type myint vector. And this is because, this is what I was just talking about, if you don't template your double ampersand, it's just an R value reference. It's no longer a universal reference. And if this universal reference stuff is not making sense to you, please forget about it and just think about R value references. But we are calling a function which does not match the, like this function, there is no function with this signature. There's no matching function call. We are calling this function bay, which takes in an R value reference. We're not giving it an R value reference. We're giving it a const L value reference. We're giving it myint vector v, which is a name which refers to some location, which is an L value. So this is just a no matching function call. It just does not compile. And a way that we could get this to compile is we could use std move. So let's take a look at that. And then, oh, I should have put that in there too. Another great bait. But because again, this has a name here, this is going to treat it as a const L value reference again. So really, if we wanted to call the R value reference version, we would need to double move it. And I'll show that real quick before I answer the questions. There we go. We finally get our R value reference. Okay, questions from the chat. Some other functions will automatically cast, right? Does the compiler ever automatically cast from L value to R value or no? So that's a tough question to answer. The answer is no, it does not automatically cast. Yes, but what student just said in chat, there are implicit conversions. So I guess the answer is the compiler will recognize when the type of the object is an R value reference. So for example, if let's say right here, I don't want to change this example too much because then we're going to get too confusing. But yeah, I'm trying to think of how to answer this question. I'm going to say you should look this up and get an answer from somebody who is not me. That is going to be my answer to that question. And look at that. Somebody just great help out from chat there. I'm sure that CPP reference page will tell you more than I could about that question. Anyways, let's really quick move through these examples. Actually, let's not. Let's just have me uncomment them and let's see what happens. Okay, so what did we get here? So if we do bar with a moved version of v, this is going to call bar with an R value reference. So bar with an R value reference. This is something that may be confusing because remember when we tried to pass an L value reference to a function that only took an R value reference, it didn't work. But when we try to pass an R value reference to a function that takes in a const L value reference, it does work. And this is just because R value references can bind to const L value references. Wait, other way around. Const L value references can bind to R value references, but not the other way around. Geez, that was confusing. Anyways, if we call Baz with the move version of V, this is just our stood forward example. So we are taking it in as a universal reference, and then we're forwarding that the true underlying type of it is an R value reference, and then the right version of foo gets called. A couple of const L value references. I guess I'm not going to go over the rest of these. This is going to take too long. Let's just get back to the presentation. Alrighty, done. Okay, we're done with move semantics. That is some complicated stuff. I promise it is important, but I think arguably more useful for a lot of you, especially if you're going into industry, would be smart pointers. And that is what we are going to talk about next. So another EECS 280 reference. You probably remember that managing dynamically allocated memory is hard. And if you forget to put a delete for every new, or you have some news in multiple different locations, you're probably going to have some weird bugs. And this is actually one of the most common gripes with C++ is that you have to manage memory on your own, and people hate it for that. Memory leaks, double freeze, dangling pointers, these are all super, super common for large applications which manage dynamic memory. Some of the most common bugs in all of software are C pointer bugs. And people think that, you know, if we had memory management under the hood from the start, we would have a lot less problematic software out there right now. So the solution is we can write a class to do the dynamic memory management for us. If we template the class correctly to take in any object, the class can just take in an object and delete the memory allocated with it when it detects the object is no longer being used. That sounds great, but that sounds difficult. So let's talk about two specific examples. Let's say we want an object that can be managed by a single pointer. If I have a class that takes in this pointer and the class's destructor, it calls delete on it, that should manage our memory for us. We have some object and we say, you know what, I don't want to call delete on this object. I don't want to even have to think about it. Let me just pass it to some object that whenever that object is destructed, it will clean up this memory for me. So that seems simple enough. It's probably not super useful, but this is what this stood unique pointer does. Takes in some type, takes in some object in a constructor, and it just calls delete when the unique pointer object goes out of scope. So here is an example. Okay, so in our main function, we're calling this add items. Add items is just going to take in this case 10, and it's going to push back a new item with that number. And this item class just is an int. That's it. It's just an int. And our unique pointer will wrap that item. So we have a vector of unique pointer of items, which is basically just a vector of pointer of items. You can pretty much think of unique pointers and shared pointers, smart pointers, as interchangeable with raw pointers, except for they do the memory management for you. So what we do is we're pushing back into our container a unique pointer with this raw pointer as the argument to the constructor. And remember that new returns a raw pointer. So we call new with some int. Let me just put it in the chat. So new item blah returns item star. So we're passing it a pointer and we're telling this unique pointer object to manage the pointer for us. So when you go out of scope, Mr. Unique Pointer, clean up that item object that I dynamically allocated. That's all that's happening here. So in main, we're adding 10 items and then we're going through 1 through 5. We are processing them. And that's just calling pop back. So what's going to happen is of our 10 items, the first 5 are going to get popped off the back, or sorry, the last 5 are going to get popped off the back. and removed from this container, and then the last 5 are going to remain in the container. So here's what gets printed. Items 0 through 9 get created when we add the items and end up creating them here in this constructor call. Then we process 5, so we process item 9 destroyed. So what happens here when we pop it from the back of our items container, there are no longer remember how we talked about with unique pointer, when the unique pointer object itself gets destructed, it will clean up the thing that it points to. So in this case, when we call pop back on item number 9, which is the backmost item in our container, it is going to call the destructor for this unique pointer because it is no longer in scope or stored anywhere. And the unique pointer destructor is going to call delete on its pointer that is internally managing. So this item will get destroyed. We then repeat for the rest of the items, and then we finally get to the end of the function. Main finishes, and our file scope variables will get cleaned up. So this items container will get cleaned up, and its destructor will be called. And of course, in the destructor for a vector, it just calls delete on its underlying array, which will in turn call the destructors for each of the unique pointers, which will call the destructors for each of the items when it deletes them. So bottom line is we don't have any memory leaks here. These objects are all being managed by the smart pointers, and yeah, no memory leaks. Pretty easy. That said, shared pointers are much more common than unique pointers. You often want to refer to an object with more than one pointer, or even if you know that you're probably not going to use more than one pointer, you want to reserve the right in the future to change your code and refer to an object with another pointer. You can't do that with unique pointers. So, and this I think is a great example for learning how these things work. The idea is if we know we want to refer to something with multiple different pointers, we can create a manager object which just knows its job is to remember how many things are referring to the object at one given time. And when 0 pointers are referencing the manager object, it knows there's no way that the user can ever access this data again. Now is a safe time for me to clean it up. Yep, these are much more useful, blah, blah, blah. These are copyable and movable. Let's get to the example. Actually, let's skip the example. Let's go to the example implementation. So let's say we have a shared pointer pointing to our item class again, and it is pointing to this new item object. Again, we're going to have a manager object. And the manager object, all it's going to do is it's going to count the number of references it has. So it's going to count the number of shared pointers that are pointing to it. And as an example, whoops, I guess what it's going to do is it's going to first say, here's the object we're actually referring to. So pointer 1 is pointing to our new item, but really it's pointing to the manager object under the hood. Let's say we create another pointer. We use the auto type because we're lazy. And we copy construct it from pointer 1. So we're now going to have a second pointer pointing to our object, manager object. It has 2 references now instead of 1. Let's say, furthermore, dereferencing a smart pointer gives you access to the raw pointer, not the manager object. Yep, so if we were to use some kind of, I don't know, dereference operator on pointer 1 or arrow operator on pointer 2, it would give us the address of the actual item object itself. And that's just because the shared pointer class overrides those operators to do what you expect. So you can treat these like normal pointers. The idea is if you have a program which manages dynamic memory, you can very likely just replace all instances of item star with shared pointer item, and your code should pretty much behave the same way. You might need to make some changes, but it's very, very easy to make the change. And I will answer those questions after I finish this quick demo because I think it will answer some stuff. So again, shared pointers are copy assignable. So if we create a new pointer, which is referring to the same underlying item object that the other 2 are, it's going to point to the manager object as well. this manager object is going to increment the references count. Simple stuff. Let's say that now pointer 2 goes out of scope. So pointer 2, the shared pointer destructs. It is no longer referring to our manager object. References count drops to 2. Pointer 1 goes out of scope. Same thing, references count goes down to 1. And finally, pointer 3 goes out of scope. There are now no more references to the item object, or sorry, to the manager object, which is just a proxy for the item object. Now the manager object knows there is no more way that the user could access this data. I am now free to clean it up. So it does exactly that. It cleans it up, and then it cleans itself up. And thus, no memory leaks. So let's look at some potential problems. And I guess first, let me read some chat. Question from chat, why don't we use these in 281 if they're used a lot in real life? The answer is just there are too many things to cover in 281 as it is. Introducing these in 281 would be, I think, too much work. And frankly, we try to convince you guys not to use pointers in 281 all too much anyways, just because you can do a lot of these algorithms and use most of these data structures without really getting into pointers. And they just introduce a lot of bugs that we found historically are not really useful for students to have to grapple with. If you want to use some shared pointers, I think you can take 482. 482 gives you an opportunity to use them. 482 is also just a good class. Another student said the manager can easily contain the object itself rather than a second level of indirection. Yes. Yeah. No, that's true. Definitely true. And I guess I should, full disclaimer, this kind of example implementation here is just an example. The true implementation of STID shared pointer may not actually do this. This is just the way that I was taught to think about them, and I think it's just a helpful visualization for learning about shared pointers. But yeah, this might not actually be the way they're implemented. Pretty sure that's an implementation specific thing. Anyways, let's talk about potential problems. So let's say we have person pointers, this person object, and it has a shared pointer member variable, which refers to the, best friend of the person in question. And the person has a name. So let's say this is in main. We have this person Albie, who I guess I'll touch on make shared in a second, but this is basically just constructing a new shared pointer. Same for Jade, Nikhil, and Mina. And let's say we set all of their best friends accordingly. So let's say Albie's best friend is Jade, Jade's best friend is Albie, Nikhil's best friend is Mina, and Mina's best friend is Albie. Is there a problem here? Well, yes, because I'm asking. And let's take a look at our, memory representation here. So Nikhil's best friend is Mina, Mina's best friend is Albie, Albie's best friend is Jade, and Jade's best friend is Albie. So these are the pointers in main. So this is the Albie pointer referring to Albie, this is the Jade pointer referring to Jade, this is the Nikhil pointer referring to Nikhil, and this is the Mina pointer referring to Mina. So what happens when we leave main? Does all of our memory get cleaned up properly? Do we have any memory leaks? Are we double deleting? Is there anything wrong here? So when we leave main, all of these pointers go out of scope. So for instance, Nikhil no longer has any pointers referring to his person object. So he will be destructed because he was a shared pointer, he was stored in a shared pointer and he had no more pointers referring to him, so his object will be destructed. Now, Mina no longer has objects or shared pointers pointing to her. She will be destructed. But we run into a bit of a crossroads here because Albie is referring to Jade and Jade's referring to Albie. They both still have smart pointers referring to them, but we don't have any pointers to them in main. So we don't have any way to access either of these data, but they're not going to get cleaned up because we only clean up the objects when they have no more references pointing to them. So if you have a cycle of shared pointers, it means the ref counts will never hit 0 and the manager objects will never invoke their destructors. This is a memory leak. Yes, the problem with the previous example is that we don't really want the best friend pointers to have ownership over the person objects they point to. They, in other words, they shouldn't keep another object alive. We just want, we really just want these pointers to be able to refer to other person objects. We don't want them to be able to keep an object alive. Some stuff from the chat really quick before we continue. Smart pointer types can't be covariant return types. I'm not sure what that means. First destructor to run is Mina's, not Nikhil's. I see what you're saying. Yes, the Mina pointer from main, I already kind of demonstrated this, I guess, perhaps in a way that you weren't happy with, but these 4 pointers, yes, they will go out of scope in reverse declaration order. So Mina's pointer will get cleaned up first, then Nikhil's, then Jade's, then Albie's. But the bottom line is all 4 of those are going to get cleaned up. And at the point when all 4 of them are cleaned up, Nikhil's is the only one which has no more smart pointers referring to him. So his object will be cleaned up first, then Mina's. But yes, these destructors will be run in reverse declaration order in main. Anyways, person object should be cleaned up even if they have best friend pointers referencing them. So there's this new class called std weak pointer, which solves this problem. Gives you a way to refer to a shared pointed object, but not actually keep the object alive. So, whoops. They don't contribute to the ref count. They don't keep the object alive, but they can tell you when the object has been cleaned up. You can use weak pointers when you don't want to assume ownership of the object. So yeah, usually only for cases where cyclical references are possible. This is a little bit more of a rare topic. You might not use these in real life, but let's say we have shared pointer 1, weak pointer, which is copy constructed from a shared pointer, which is legal. And then we have shared pointer 2, which is copy constructed from a shared pointer. So our new implementation has a references count and a weak references count. And let's see what happens when various things go out of scope. So S pointer goes out of scope, now only 1 reference. S pointer 2 goes out of scope, now 0 references. And we're not going to change any of our behavior. So when there are 0 strong references, the manager object will clean up the memory. And if at this point you try to access the data with the weak pointer, there isn't, you can't access the data anymore. And the manager object can tell the weak pointer, it can safely tell the weak pointer, basically, there's nothing here for you to access anymore. I don't know, try again or do something else. But then when weak pointer goes out of scope, only then, when there are no weak and strong references, can the manager object be cleaned up. So yep, if 0 strong references, clean up the manager object. If 0 strong and weak references, clean up the manager object. Pretty straightforward. So now if we have our person struct, we can solve our memory leak problem by changing the best friend pointer to be a weak pointer instead of a strong shared pointer. So, yep, and I even discussed this. The destruction happens in the reverse order of construction. So to touch on what Brian said in the chat there, because the Mina pointer was just constructed last in main, it will be destructed first. So pointer goes out of scope. Suddenly there are no strong references referring to Mina. Mina gets destructed. Nikhil still has the weak pointer referring to the Mina manager object, but if he tries to access that weak pointer, it will basically tell him this object went out of scope. Then the Nikhil pointer, because it was constructed second to last, so no more strong references here, it will be cleaned up. Then the Jade pointer, which now no more references here that are strong, gets cleaned up. Finally, the Albie pointer. And at last, we have our 0 memory leaks. Another yellow slide. Can assign shared pointers to weak pointer variables to instantiate them. And the big caveat is that you can't actually access the reference item with a weak pointer. So the way that we get around in our previous example, so at this point, Albie still has a weak pointer pointing to Jade, but it's just pointing to Jade's manager object, and the manager object will be able to tell this weak pointer that the object itself no longer exists. The way that that actually works is that it requires, the weak pointer requires you, oh geez, I need some water. It requires you to create a shared pointer from it before you can access the variable itself. So you can't actually use a weak pointer like a normal pointer, but you can do that with a shared pointer. And this function weak pointer lock returns a shared pointer to the managed object if it exists. Otherwise, it will return a null pointer. So, I think I'm going to skip this slide. Basically, yeah, I'm going to skip that slide. Feel free to take a look at this in the slide deck if you want to really take a good example. One more warning. Regular pointers, the star variety, have no mechanism of detecting whether or not the pointed to object is still around. Like we said, big source of bugs. Very not good. C++, not fun. So the advice is you shouldn't mix regular pointers with smart pointers. If you have some item class that's being used in some large program, you should probably only refer to it with raw pointers or only refer to it with smart pointers. If you have some object that is being pointed to by both smart pointers and raw pointers, as soon as the smart pointers get cleaned up, the object will get cleaned up, but the raw pointers will have no way of knowing that the object was cleaned up. So in general, you should either change all of your references to smart pointers or you should probably just leave them. Yep, and if you must, you can use shared pointer get to get the raw pointer to an object, although this is not really recommended because this is just doing the same thing that we told ourselves not to do, which is mix raw pointers with shared pointers. And you saw a little bit of this earlier, but some people believe that any amount of manual memory management is too bug prone to tolerate. And the idea is if we don't use new or delete anywhere in our code, it is very, very hard to introduce any memory leaks or any memory related bugs. So there are these functions which allow us to, that allow the constructors of the shared pointers or unique pointers to create the object for us. So we can use std make shared or std make unique. And instead of taking in an item pointer itself, it actually takes in the arguments to the item constructor, and it will call the item constructor with new. And then it'll return a smart pointer to the constructed object. So instead of shared pointer with my class, we can think of this as item, and putting new in the constructor list for the shared pointer, we can just do shared pointer my class is, constructed from make shared of my class. And we give the make shared function call our 3 arguments, or auto pointer equals make shared with our 3 arguments. Cool. So taking a step back a bit, and please feel free to ask questions in the chat if you want. I think this idea is a bit more easy to mentally grasp than move semantics, but I'll pause for a second here for any questions. Okie dokie. So RAII, one of the worst names in all of computer science. This is terrible. RAII stands for Resource Acquisition is Initialization. Blah, that's terrible. The idea is because C++ enforces that when an object is constructed, when the object leaves the scope, its destructor will be called. We can kind of take advantage of this to acquire some resource in the constructor of a class and release the resource in the destructor of a class. And because we know for sure that the compiler guarantees all local variables destructors will be called when they leave their frame, we can guarantee that no matter how we leave this function, whether it be from a return value, whether it be from just hitting the end of the function, or whether it be from like an exception, we can guarantee that our destructors will always be called. So if we grab some resource in our constructor and we release it in our destructor, no matter how we leave this function, we can guarantee that we've cleaned up correctly. That's the basic idea of RAII. Yep, basic pattern in constructor, acquire the resource, and the destructor, free the resource. So here's a weird RAII example that I took from a class that I took this, I guess my sophomore year. But let's say in C++, we saw a bit of this in project 4, but you can change like the flags for cout. So, geez, burping. But you can do things like set the precision. You can, I don't know, give it like specific formatting flags if you want. I don't know, stuff like that. But what we can do is we can write an RAII class to, whenever we change the flags of cout, remember what the old flags were and reset them as soon as we leave the function. So our function foo here, all that it's doing is in the constructor, it is taking the cout flags and it is storing them in this old flags variable. And it's taking the precision and it's storing it in the old precision variable. And then in the destructor, it is just restoring those. So it's setting the cout flags back to what they used to be, and it's setting the cout precision back to what it used to be. And using RAII, we can construct an object, change all the cout precision, print out whatever we want, and then guaranteed by the time we leave this function, the old flags will be restored. So actually pretty useful. And the reason that it's pretty useful is not really demonstrated in this simple example, but let's say we have some function that could throw an exception. If the function in question throws an exception, the formatting will still be restored if we use RAII. But say at the end of the function, if we just did, instead of this, whoops, can't use VS Code shortcuts, but instead of the end of the function, we just did, old cout.flags equals old flags. If we did something like this and this function threw an exception, this line of code wouldn't be run. But because we're using RAII and the compiler guarantees that this object S will always have its destructor called, then even though there's an exception that could be thrown here, we are safe, and no matter how we leave this function, our flags will be restored. So yep, we get to forego an ugly try-catch block here. Yeah, pretty neat. RAII is actually pretty cool, especially if you're doing multi-threading code. Other weird cases, yeah, I'm totally going to skip this slide. Actually, no, I won't. It's pretty cool. But the compiler inserts these destructors at the very end of the scope where the object is declared. So in this example here, I guess, the shared pointer PTR will be destructed basically after this return line. So for a weird example of a function which is recursive, we actually don't get tail recursion here, because after this return finishes, the pointer PTR actually needs to be destructed. So the compiler inserts the destructor call down here, and only after this return call happens does that destructor call happen, which means that we can't reuse this stack frame in this particular recursive example. So super weird edge case, but the bottom line is any non-trivial destructor, I think that's the official term they use, which doesn't mean that much to me, but any non-trivial destructor will necessarily have its destructor called at the end of the stack frame. And this could have other side effects that you might not be aware of. Okay, trivia number 3. And feel free to take a break or step out and go to the bathroom or something. We're going to take like a 5-minute break after this. But trivia number 3, geography. This highlighted region of South America, specifically Chile and Argentina, bordered by the Colorado and Barrancas rivers, was inhabited by small agricultural and hunter-gatherer indigenous communities until it was colonized by Argentina and Chile in the 19th and early 20th centuries. It also shares a name with a popular outdoor clothing brand. What is it? Does anybody have any guesses? No wrong guesses. You guys are totally right in the chat, by the way. This is Patagonia. Super beautiful. All right, another geography slash world related one. Which of the following is the largest city by population that is not the capital city of its respective country? Tokyo, Delhi, Shanghai, Sao Paulo, or Mexico City? Who's got the answer for me? No bad guesses. Lots of Shanghais in the chat, and you are totally correct. So, and these numbers are from, I don't know, I think like 2018 or something. So this actually might have changed, but bottom line, Tokyo, I believe, still the biggest city in the world, but it is the capital of Japan. Delhi, capital of India, also massive city. Shanghai, not the capital of China, that would be Beijing, and it is massive. Then Sao Paulo, Brazil, and Mexico City, Mexico. And these, I believe, are the 5 biggest cities in the world, at least as of 2018. So interesting facts. Okay, and before we get into lambdas, these are definitely the biggest 2 topics. The rest of these are a lot quicker, but let's take a 5-minute break. So let's get back at 3:55 if you want to be up to date. And, if anybody needs to use the bathroom or take a quick breather, hop off right now, and I will see you guys back at 3:55. Alrighty. Hopefully that was an extremely restful break. And actually, let's give it one more minute and then we'll get into Lambdas. All right, Lambdas in the functional library. I recently trimmed down this functional library section a lot. And I'm going to skip over a decent chunk of it because I think Lambdas are really the only important part of this section. So bottom line, Lambdas are anonymous functions, and that probably doesn't mean anything to you, but brief justification, sometimes we write functions that we're only going to use in one place. So why would we introduce names for these functions if we don't need to? Why would we pollute the global namespace or the file scope namespace with these functions if we do not need to? We could just simply, if we wanted to, we could define them in line, right where we're going to use them. We could write these functions. And thankfully, C++ and I think every other major programming language allows us to use lambdas, which are this exact thing. So they're anonymous functions that can be defined and used similarly to function objects. They're anonymous because by default they're nameless. You usually just define them directly where you would use them, and they are usually only used in line, not stored. So syntax and use, some of the weirder syntax in C++. Square brackets around something called a capture list, then parentheses around parameters. This is normal for a function, and then curly braces around the body. The body can have any number of statements in it, just like any other function. So the capture list, I will touch on this in a lot more detail in a couple slides, but you can think of these as like member variables for a function object. If there are any, I guess, data points that need that the body of the Lambda needs that it shouldn't take in as a parameter, or if there is some value that will need to be updated or something when this Lambda is called multiple times, you'd want to put it in the capture list. Again, don't worry about that too much. I'll touch on that a bit later. And the parameters in body are just like any other function. So let's say we have our example, vector of items. Let's say the items vector gets populated, and we call std sort on items begin, items end, and we pass in our comp func, which just takes in 2 items and returns, x less than x. So the problem here is not that this doesn't work, it's that we don't really want this comp func. We don't need it. We just kind of want it to be we just want it defined inline here, and it's kind of annoying that we have to define it in the file scope. So this is kind of a weird example, but if we wanted to define some other function, comp func, let's say we were comparing items in multiple different ways, now we would no longer be able to use this name. And more importantly, somebody who's reading this code might, see this and wonder, oh, where is this used? Like, is this really important? Do we really need this? And the answer is we probably just want to define the function inline here. So the way we can do that is just use a lambda. So instead of using our comp func function, we can just write a lambda with nothing in the capture list. So empty square brackets takes in a const item by reference and a const item by reference. And then in the body, and you can do this, you can put it on multiple lines. We just return ax less than bx. And if you take a look, this is the exact same code as our comp func. And instead of defining it outside of main, we can define it in the line of code that we're using it. And this is super, super nifty. It feels cool, and it just looks nicer because you can read exactly what the sort is going to do without looking anywhere else in the code. Ooh, neat. You can write templated lambdas. I did not know that. C++ 20. Neat. I wonder how many places have already adopted C++ 20. I let Copilot write lambdas for me. It's easier. I have not played around with GitHub Copilot, but it seems really good. Anyways, capture lists. So this is the weird part that I was thinking that I kind of avoided earlier, but the functions in C++ are statically scoped. So what this means it means that where the function itself is defined, so in our previous example right here for compfunc, where the function is defined, it has access to all of the variables that it can see at the time of the definition. So let's say we had, I don't know, int AAA equals 5, right? Because when we defined compfunc, it has like visibility to AAA, we can legally use AAA in this code, right? So we can do something like cout AAA. And this is pretty intuitive for most of us. Oops. Oh, geez. Get back to where I was quickly before I lose everybody. Okay, so they are statically scoped, which means you can see whatever variables are, I guess, within your visibility at the time of declaration. So lambdas do not have this quality. What that means is if we had, if we had AAA up here, so we had int AAA equals 5, we would not be able to just use it within this lambda here. We would need to do something different. So let's go back to our code, go back to our presentation rather. You must capture things manually, and that's what this capture list is for. So in the capture list, that's the square brackets at the start of the lambda. If you just put an equal sign, it means capture all variables that the lambda uses by value. So only the ones that it's using, not the ones that it sees. Same thing with this ampersand, it captures all the variables that the lambda uses by reference. But if you want to capture specific variables, you can do it by name. So if there's some var1 that you want to capture and use in the body of your lambda, you can capture it by reference by putting an ampersand next to it. If you want to capture it by value, you can just write the name of it. And you can, because it's a capture list, you can, append as many different things as you want here. And then, some weirder examples, you can capture var1 and var2 by value, and then put an ampersand here to say capture everything else that I use by reference. And the compiler is smart enough to see what you're using in the body of your lambda and only capture what is actually needed. So let's do another example real quick. Have some vector nums. Let's say it gets populated with n numbers. And we have some mod class here. So this is, we're going to eventually replace this mod class with a lambda. And this is just a functor. And all it does is when the parentheses operator is used on it, it takes in a value by reference and it sets it to, I guess, the number of times that this function has been called. So when we call transform with nums begin, nums end, and we put the output in nums again, what it's going to do is it's going to set nums to 0, 1, 2, 3, 4. And mod class, we still have access to our I variable because we still have access to our I or our mod class object, and we can print out that state. Well, thankfully, we can do all of the same stuff with capture lists and lambdas as well. So we have the same thing, vector of nums gets populated. I guess we don't need that because it gets populated right here. We have some local variable I, we call transform, and instead of using some mod class parentheses operator, we just take in a reference, and this could be int, but I've auto typed it because that's more fun, value, and we do the same body, so val equals I++. And where is this I coming from? We can't just see it here. Well, yes, we can because we captured it by reference specifically. So yeah, this has the same result as the code on the left, and we can still print out I to get our local state. So I guess I won't. Oh, perfect. I was just going to make this edit. But what happens if we just capture it without this ampersand? If we capture it by value? Does anybody have a guess for what will happen based on this code if we don't capture I by reference? That's a good point. Actually, yeah, good point, Brian. I did not this should just be for each transform. I mean, I could write this so it returns it, but this still works, I think. Some guesses. They will all be 0. Undefined behavior. Undefined. Geez, undefined behavior. Or it will print 0. And the answer is it no longer compiles. So the Lambda call operator is const by default, which means that we can't modify any of our member variables, which is the things that we've captured, unless we explicitly say that our Lambda is mutable. And this is super annoying. This is why this is a yellow slide, because it's very weird. What you would think would happen is it would just do 0 every time because we're capturing this by value, or it would increment all the values, and then at the very end, our I, which we captured, would still be 0. But yeah, we need to mark the Lambda as mutable to even get this to compile. It's the bottom line. So let's say we set it as mutable and we capture this by value. Now, whoops. Now we will get the behavior that we more or less expect. So we're capturing this by value. So you can think of it as making a copy and storing it as a member variable in some function object. We still get the behavior that we want. And internally, this stored I will still be incremented. So we'll still get 0, 1, 2, 3, 4. But at the end, when we print out our local variable I, which was initialized here, because we didn't actually modify it, we modified a copy of it, we are just getting 0. So guesses in the chat, all very good. And I'll touch on this very briefly. We don't need to specify the return type of a Lambda. So I don't think I gave you any examples. I guess I did with the here. So we didn't need to specify that this Lambda returned a bool. The compiler was able to interpret that for us and basically specify, and it checked that it was compatible with where we were using it, and it does that automatically. But with other functions, we need to specify the return type. So the compiler is usually smart enough to do this for us, but it doesn't always do that. So for example, let's say we have some Lambda, takes in a double. If D is less than 0, it returns 0. Otherwise, it returns D. And in the same line of code, when we declared it, we are calling it with 5. So you can do this. It's very funny. You can lead to some very interesting one line of code. But bottom line is here we have 2 points of return. We have a return here, which returns 0, which is an int. And we have a return D down here, which is a double. So this doesn't compile because the compiler can't determine the return type. It doesn't know if it's an int or a double. What we can do, though, is we can explicitly tell the compiler with a trailing return type, which is just this arrow operator and then the type name, that this is going to return a double, and now this compiles. Okay, final thoughts. You can also capture a Lambda in a variable and use it multiple times, but you must use the auto type. Let's use the type auto. Well, changing that for the future. You must use the type auto because the C++ standard, at least as at the time of these slides, does not specify what the type of Lambda objects is. So, for example, if we didn't have the word auto here in func when we were trying to store this Lambda, it would be some internal mangled type, which we would not know at the time of writing this. So anyways, we can store this Lambda in func, and then we can call it like any other function. We can call func at 5, and it will print 6 because it's just printing x plus 1, and we passed it 5. You can even pass it into a templated function in this manner. And this is, I guess, how things like std sort work. They take in a templated final parameter, and you can pass in functions, which will then take on the name comp or things like that within the body of std sort. So yeah, here's a good resource for understanding more about Lambdas. I'll paste it in the chat really quick. And that bottom funny line of code down here, I just think is so funny. It does absolutely nothing, has no side effects, but very cute. Who doesn't love a good weird line of code? Okay, functional library. That is funny to know from student chat. That line of code if you were to do it in the C++20 version with the templated list, would not be valid. Anyways, functional library. I'm going to speed through this. I think this stuff is not useful. If you wanted to refer to functions before the functional library, like in C, you had to use function pointers, which are super ugly. And the way that you declare a function pointer variable is like this: return type of the function, then parentheses star, the name of the variable that you want to store the function pointer in, parameter, or sorry, closing parenthesis, then open parenthesis with all the return types. So for example, if we have some function foo, which takes in an int and a const string by reference, if we wanted to refer to foo, we would do void, because it's a void function, parentheses, star, var name, close parentheses, open parentheses, int, const string reference, and then assign it to the address of foo. Ugh, what a terrible line of code. Who would ever want to do this? And who would ever know to do this without looking it up every time? And this address of operator is optional. You can just do foo directly there. Then what we can do is we can then dereference our function pointer and call it with int and const string reference and actually get the effect of calling this function. You can also do it without dereferencing the function pointer, so you can just call it like a normal function. Anyways, this is all before the functional library. Now there is this thing called std function, which allows us to do all of that without relying on these outdated C features. And the declaration anatomy is very similar to a function pointer, but it looks a lot nicer. It is just std function, and then as template parameters, but it seems weird to me, you do the return type and then in parentheses the parameter types. And then you can give it whatever variable name you want, and it looks more or less like a pretty C++ version of something that was ugly. Then you can call the function as you would normally. And you can do fun, bold on fun things with these, like store them, store any functions with the same parameters and return types in a container, and then call them. Ooh, super fun and useful. I can think of exactly 0 examples where it would be useful, but maybe you guys have better imaginations than me. There's also something called std bind, which allows us to specify the parameters to a function call ahead of time before it is called. This actually is useful in some scenarios. I think there are some design things that you cannot get around without doing some janky bind shenanigans. So what you do in this case is you call bind with the function name, and then you bind certain subset of the arguments ahead of time. So let's say, for example, we have our function, which is a void return type, and it takes in no parameters, func1. So the key thing here is this variable here, the std function variable, is expecting a function which has no return type, void return type, and takes in no parameters. So just crushingly, foo takes in 2 parameters. So we can't set func1 to foo. But what we can do is we can set func1 to a bound version of foo, which already has the first 2 arguments specified. So let's say we have f1, which takes in an int a and an int b. We can then bind a and b to the first and second argument of foo. And now func1 is a function that takes in no arguments and returns void. But really what we've done is we've just specified the first 2 arguments ahead of time. And this is actually pretty neat and useful in some scenarios. So let's say later on in the same CPP file, we call f1 with 10, 9. What it's going to do is it's going to eventually call bind on foo with 10 and 9. And then our foo function call, our func1 std function is basically primed to go. We've already given it the parameters. We're just waiting to call it. And thus we can then call it, and you have the effect of calling foo with 10, 9. But really, we passed 10 and 9 to the function a lot sooner than we called it. And this binding potential is prevalent in, I think, most, if not all, other programming languages. And it was only recently introduced when the functional library was introduced to C++. So super neat. Not super useful, to be honest, but in some scenarios you might. You can also just specify some of the parameters, not all of them. So what you can do, let's say you want to specify just the second parameter. Is that the exact example that I'm giving? Yes, it is. Neat. Good for me. What we can do is we can use these things called std placeholders. Ew, gross again. But let's say we have func2. This time, instead of taking in no parameters, it takes in one int. And we want to bind it to foo ultimately, which takes in 2 ints. So we can give it 1 int ahead of time and then give it 1 int at the time that we call our function. So using namespace placeholders, we can give std bind foo and then a, and then this _1 thing, which is placeholders, really std placeholders : under 1. And it's going to bind a to be the first argument of foo. So when we call f2 with 5, 5 will be bound to x because we passed it. We said a and let a be the first argument of foo. And then we can call func2 with the remaining argument, which is going to be our y, and it's going to be 4, and then it'll print 5, 4. And you could also, if you wanted to say, give it the second argument, you could say a and then _2 to bind the second argument instead of the first one. And then when you call func2 with 4, it will pass that in as x. Yeah, so that's more weird stuff. Placeholders specify the order of the parameters that have yet to be specified. They're required when you don't bind all the args at once. So whenever you're not binding all the args, you need to use these _ placeholders. Can also rearrange the arguments in the final function call. I don't know, interesting stuff like that. I'm not going to go over this example. Yeah, so this is another really, really weird thing. Again, don't pay attention if you don't think you're going to ever use this stuff. But the arguments to bind are always copied or moved. They're never passed by reference unless you wrap it in std ref or std cref, the C for const. Yeah, super weird. But basically, if we do this bar func right here, let's say we bind bar and then some local variable and then 5. And what bar does is it just sets the second parameter to the first parameter. So what's happening here is we're passing in local variable and 5. And what we expect bar func to do is set 5 store 5 in our local variable. But really what happens is, even though this is a reference parameter, it actually prints 0. What we need to do if we want to actually take advantage of binding a reference parameter, we need to wrap our local variable in ref. Super lame, really weird. Okay, mem function, the same thing as std function, but it works on member functions, and the way that member functions work in C++ is they take an implicit first parameter, which is the pointer to this object. So mem function basically takes care of a lot of that for you under the hood. Skipping over that. Okay, singleton pattern. This is one of my favorite things because it touches on design patterns, and I think design patterns are arguably one of the most important things you can learn if you're going into industry. So this is going to be a shocker to some of you, but for most projects, the majority of their life cycle is spent in the maintenance stage. Once the software has been written and released, developer time is spent fixing bugs and adding new features on top of existing functionality. And this comprises the majority of a project's life cycle for most projects. So how this relates to you, most of your time as a developer will probably be spent reading existing code you did not write. And a lot less of it than you think will be spent writing new code, which is, that was a surprise to me when I learned that. Anyways, you'll occasionally be asked to update that code, but only after you've understood it and the impact your changes will make. So, therefore, it is extremely important to not only write code that works and is efficient, but code that is extensible, easy to add to, maintainable, easy to change, and readable, easy to understand, and thus design patterns. And global variables. This is an anti-design pattern. They are not what we want. What is wrong with them? anybody can change them in any way that is desired. So if you write a global variable that's only supposed to be used for one purpose, somebody else on your team or somebody who's using your software may change it and ruin everything you've written. It's very unclear and not easy to decide the following, which is, when is the initial value determined? What if you need a global variable that has the initial value determined at some point later in the program? You have some declaration for your global variable, and then you're only assigning to it somewhere else in the code. That could get a little bit hairy. Somebody might read the code and not be able to find where you've set the value. Yeah, weird stuff like that. And yep, if the initial value requires runtime computation, where does it get initialized? How do you make sure it's initialized when you want to use it? Blah, blah, blah. So the Singleton pattern basically allows for better globals. If we need the following, exactly one object of a class, which is globally accessible, but only in certain ways, it's relevant everywhere in the system, but there should only be one of them, and its creation, initialization, and destruction must be clear and well-defined, then our answer is going to be use a Singleton object. And they're more extensible, maintainable, and readable global variables. So one more example here. And this one I think is really good. If you are curious about using the Singleton pattern, I would recommend stealing that code for yourself, because I wrote the Singleton pattern myself once. And then, once you write it enough, you just kind of understand how it works on your own. Okay. This is also going to touch a little bit on timer shenanigans in C++, which is pretty interesting. But that's just because I needed an example to make a Singleton with. So the hallmarks of a Singleton class. There is a static getInstance method which creates the Singleton object if it doesn't already exist and returns the Singleton. So first thing to notice here, our global variable is stored in some class. This is good just because it allows us to control when the object is created and destroyed. We can do things like set certain methods to be private so that random people can't call them, or users of our code can't modify this value without us controlling how that's done. So first thing to note is that the constructor is private. So nobody can create one of these singletons except for the code which is within this class. And the reason for that is because we don't want somebody to create another one of them. We only want one of these things. It's a singleton. So we're going to make it so nobody can create one of them. Except for the code within this class, which you'll see this line will create exactly one instance. The destructor is also private, so we don't want anybody to be able to delete the object either. So let's say they get their hands on this Singleton timer object. If they call delete on it, we do not want to actually allow that. We want them to only be able to use it, not to delete it. So we say you can't do that. And we also say you can't copy and move it. And the way that you do that in C++ is by writing out the signature for the various operators and then writing equals delete. What stops you from calling getInstance twice? A great question, and I will get into this. So the way that this getInstance function works, and this is the idiomatic way to do it in C++ with, I guess if you wanted your singleton to work by returning a reference to the object as opposed to a pointer, if you wanted the singleton to return a pointer, there is an example down below for how you could do that. I think it's less clean and requires a little bit more knowledge to understand. But the idiomatic way to do this, to return a reference, is to create a static local variable in this getInstance function. And the way that static local variables work are the first time that this function is called, this line of code will be run, but it will not be run any other time. So because I put static here, if I didn't put static here, this would create a new object each time this function was called. But because I put static here, this line of code will only be run the first time this function is called. And then it will be skipped every other time it's run. So this instance basically lives as a local variable in this function, but because it's a static local variable, it will stick around forever. Yeah, so this will only be constructed once. And this line right here is doing a default construction of this variable instance. Okay, so then we have this function, which is print time since creation. And notice that this is not static, so you need to actually call it on an object of type mySingletonTimer. So you can imagine that somebody might do get instance dot print time since creation. And I guess the thing that I should have noted is in this constructor, we're just setting a start time. So we're saying system clock now, this is when the object was created. And then this print time since creation, we'll just print the number of seconds that have elapsed since the object was created. Okay, so let's go to an example. So, whoops, probably want to get example A going here. So let's uncomment that, make singleton. So what this is going to do is give us the reference mySingleton object. We're going to store it in a local reference variable called timer. And once we've got the instance, we're going to print the time since creation. And because we're calling these things so close in quick succession, we should expect about 0. So start of main, creating timer singleton, which is just our constructor, which was called during this line. Then time since creation, 0 seconds, because we just created it just then. Then the end of main, and then after main ends, we destroy the singleton timer. Now let's say, as the student alluded to, what if we have this line of code like 9 times? What if we do that? I don't know, Q, R, S, T, I don't know, Q, sure, we'll do something like that. Will multiple singleton objects be created? Nope, only created once. And that's just because that static line only gets run once, and once it's created, we're just returning the same instance every time. So we're returning the same data every single time this function is run. The only difference is the first time is the only time it's created. So if it's already created, these lines will just give you a handle on the existing data. So we could do something like this, get instance, and then, instead of calling timer, print time since creation, we could do something like, use Q instead. Because they're both referring to the same data here, this is going to give us the same output as before. The same timer, 0 seconds since creation. And let me get rid of this, and let's just go to example B. Or the second part of example A, rather. So there's this function which just makes this thread go to sleep for however much time you specify. So let's say 2 seconds, and then we can print the time since creation there. So time since creation, 0 seconds, then it waits 2 seconds, time since creation, 2 seconds, end of main, destroys the singleton. Great, just like we want. So now let's say instead of using timer, what if we get the instance and print the time since creation? Does anybody have any guesses based on what we've talked about? What is this going to print? The same thing. Yep, you're all totally right. And this is why the singleton design pattern is so cool. So it creates the singleton. And even though we're not referencing the same reference variable when we call print time since creation the second time, because the object itself is maintained by this mySingletonTimer class, when we call get instance, we're really getting the same object that this timer reference is referring to. So when we print time since creation here, it's still the same object that slept for 2 seconds. So yeah, that's the power of the singleton object, really. Now let's take a look at example B. Let's see what we got here. Yep, this is pretty much the same thing we just discussed. It's going to create a singleton here. This is the first time this function was called, so it's going to create the object, print the time, which is 0. Then it's going to do it again, print the time 2 seconds later. Easy enough. Okay, so now I've added a little bit more of a complicated example just to show some power. the power of the singleton here, because these examples, really what you would use a singleton for in a real life scenario is you would have some large program which accesses some shared state in many different ways. So because we only have one file here, a singleton doesn't really make sense. Like we could have defined all of this code in main and it would have been totally encapsulated, but more likely you're going to have some module that's being used by a bunch of different areas of your code base. And thus, it's difficult to see how these things would be created and destroyed, which is why a singleton's useful. So here's our example. If flip coin, and flip coin is just a function up here, which will print heads or tails based on a 50-50 probability and return true or false. Using random in any programming language context is like one of the most satisfying things. So I think it's fun to play around with that stuff. So if it's heads, we will create the timer immediately. And really we can just do this, right? We're not actually using that timer there, but we create the timer immediately if the coin is heads. Then we sleep for 2 seconds and we get the instance and print the time since creation. So does anybody have any guesses for what will be printed if the coin is heads and what will be printed if the coin is tails? Okay, so if the coin is heads, I see it would print 2, and if the coin is tails, it would print 0. And yep, I totally agree with you. And I tried to fool you with naming timer the same thing both times here, just to make you think maybe it was already initialized up here, but nope. This is just going to grab a separate reference variable to the same instance object. So let's make singleton, let's run main, coin is tails, so it's going to wait 2 seconds, then create the singleton, then it's going to print 0, and then it's the end of main. Let's try it again. Hopefully we can get heads. Coin heads, perfect. Created the timer on this line, slept for 2 seconds, then printed, and time since creation is 2 seconds. Okay, and let's say I remove this line. This is just another random thing that I think is pretty interesting. If I remove that set rand line, the random seed, which determines all of the calls to rand functions, doesn't change every time. So what that means is this coin is always going to be heads. Unless I recompile, the coin will always be heads, which is pretty interesting. Now, if I put this back in, that will change even without recompiling the code, because I'm setting the random seed to be the number of seconds since the epoch, which is changing every time this code is ran, because time is continually counting up. So coin is tails, coin is tails, coin is tails, coin is heads, even though I didn't recompile. So pretty neat stuff there. And yep, if you want to scroll down in that example to see how you could use a pointer version of this get instance function as opposed to a reference version, it's pretty annoying because you can't have the singleton class itself delete the pointed to object, but take a look at that, and I've wrote some comments in the replit, so you can hopefully get that explained to yourself. Okay, moving along. Singleton pattern over. Let's speed through tries. Full disclaimer, tries. All of this section is going to be yellow because tries are very interesting and they're very cool to flex in an interview, but they are totally not used in real life. Nobody ever uses these. Maybe there are very specific examples for where people use them, but they're super, super cool. You can think of them, I guess I don't want to spoil anything. They're a node-based data structure for storing strings. They have a very simple design, and they are the theoretical lower bound for efficient insertion and lookup for strings. And in my opinion, they are super clever and cool, and they're pronounced a try. I don't make the rules there, so I apologize to everybody who wanted to call it a tree or something. So instead of storing words separately, so remember, this is just a data structure for storing words. And instead of storing the words separately, let's store characters so that words with overlap don't have duplicated data. What this means, instead of storing app and apple separately, why don't we store app and then we store LE after it? And we can also, so we know that app is still a word in our data structure here, we can note that that P is actually the end of a word. And we can note that the E is the end of a word as well, but the rest are not. So for example, if we push app, apple, and bat into our try might look something like this. And I'll get into an exact implementation in a second here. But we would have APP. We would note that this P is the end of a word, but we also have an LE after it. So if we're looking for apple, we could see APPLE. If we're looking for app, we would see APP. But if we look for like A, we would see A, but we would know, oh, this isn't the end of a word. So A is actually not stored in our try. So for each letter, we're going to store whether or not it's the end of the word, like we talked about, and we're going to store pointers to the n possible children nodes. And usually n is 26, the lowercase English letters here. And again, this is usually theoretical because there are not that many instances when you can actually guarantee these things. And this is the reason that this data structure even works at all is because this is a constant number. So tries work best when the set of characters is limited. You can use a fixed size vector or an array of pointers instead of like a hash table to look up the next index. So I think, yeah, this is 4-slide design there. But we can store null pointers whenever there's no children, so we don't unnecessarily allocate these nodes. So here's a try node object. If we had a try class, which was a node-based tree like we saw before, we store whether or not it's the end of a word, and we store a pointer to 26 other try nodes, which can be null pointer. So when we allocate it, it would look like this instead of being null pointer as it was previously. And I think, as always, the best way to learn this is through an example. So say we have some try node, which is the root, and we've got nothing in it so far. Let's say we insert app, same as our previous example. First thing we do, we would want to check if children is null. And if children is null, we would need to create this 26 length array. And because we're inserting app, the first character is A. So we allocate a new node at position A. So this is the try node, which is A. It's not the end of a word, has no children yet. So because it has no children and we still have more characters to insert, allocate 26. We have a new node at P because the next node is P. Then not the end of a word yet. We still have null pointer for children. So because we need to insert one more P, we need to allocate 26 more. And yep. Okay, yep, perfect. Then we have our second P, which we say it's the end of the word, it's true. So we don't need to allocate any more children because there are no more characters after this P. And done. So we have our app in our data structure. Now let's say we insert bat. Similar thing's going to happen. At B, we're going to create a new node, no children. We still need to insert an A, so we'll do that. And it's another 3-node kind of situation here. Now, if we want to insert apple, though, this is where you can actually take advantage of this overlapping characters design. So what we're going to do, we're going to check the root. We're going to say, hey, do we have any A's? Yep, we have an A. We're going to check this A node, say, hey, do we have any P's? Yep. Do we have any P's? Yep. Do we have any L's? Nope. There's actually no children even. So we allocate the children, create a new L node, allocate the children there, create a new E node, and we say this is the end of a word. So this is the basics for how a try works. And you could implement one pretty easily. I don't think it would take too long. Anyways, complexity, and this is where it's super cool. Insertion, lookup, and removal are all O of K, where K is the length of a string. And this is the theoretical lower bound for any string data structure, because you always need to look at every character of the string to see if it exists or to insert it or to remove it. So this is as good as it gets. And is it any better than a hash table in practice? Yes, because you don't have to do a hashing operation. but can a hash table in theory, or not in theory, in real life, does a hash table do good enough for, these complexities? Yeah, a hash table does, close enough to these to where most people aren't implementing their own data structures just to store strings. They're just using hash tables of strings. Yeah. So if you want to remove something, you can either find the word and set the end bit back to false. Does the SCL have tries? No, I do not believe so. Somebody can look that up if they want, but I'm 99% sure it doesn't. And the other advantage of a try over a hash table is that, of course, the try does not store this duplicated data. So you could set the end bit to false if you want to remove something, or you could find the word and then recurse back up the try until basically you have removed everything which has no other children. Yep, these are the theoretical lower bounds. You can't get any better than this. We claim hash tables are O1, insert, lookup, remove, but of course you need to hash the strings, and hashing the string requires that you look at every character. Or at least checking that the characters are equal if you have a hash collision will require that you look at every character. So hash table also doesn't have O of K levels of indirection. Not quite sure what that means, but if you want to elaborate in the chat, I can maybe respond if I know how to answer it. Anyways, hash tables are also O of K for these three operations for the same reasons that tries are. But there's a heavy memory overhead, even though we're taking advantage of these non-overlapping. Yes, lookup in a try, student said lookup in a try involves following O of K pointers, correct. Memory access is slow, to the heap even more so, correct. Yep. Yeah, I don't disagree with anything you're saying. These are theoretical lower bounds, and also, I mean, hashing functions are slow as well. So really, it's pretty good no matter which way you cut it. But yes, there are some slow parts of each of these. Anyways, heavy memory overhead. There's an array of 26 pointers per node. So even though we're only using one of the 26 children of this A, there's still 26 of them allocated. So, we are getting around storing the duplicate characters, but we are also storing a lot of pointers when we maybe don't need to. Okay, polymorphism under the hood. This is my favorite topic to talk about. And you will probably only find use in this content, I guess, if you are working in a very object-oriented setting, which at least in a lot of C++ contexts, you probably are, because that's where C++ really shines. So how does inheritance and polymorphism work under the hood in C++? Let's get into it. There's a parent-child relationship between classes in an inheritance hierarchy. So the child inherits all the public and protected members from a parent, and we can say that a child class object is a parent class object. And this just means that a child pointer can be used anywhere that a parent pointer is expected. This is the Liskov substitution principle that you may or may not have learned in 280. So the question is, why is this the case? Yeah, why can you use a child pointer wherever a parent pointer is expected? So let's get into it. The anatomy of a C++ object. Let's say we have some struct. It has an int A, an int A2, and a double A3. And A pointers, or I guess this is the object in memory. This is what the A object in memory would look like if we created one of them. It would have simply the data members packed together. That's all it does. And any pointer to an A object points to the start of the memory location. And if you wanted to access a field through a pointer, all that happens is under the hood, the compiler just inserts some byte offsets to ensure that you're getting the right thing. So if ints are 4 bytes and you want to get A2, you just need to skip over the 4 bytes from A1 and then get the 4 after that. And under the hood, the compiler will do all that for you. Bottom line though, every pointer pointing to an A object points to the start. Yep, contiguous in memory, there's sometimes padding, CX through 70. The data members are stored in the order specified in the class definition, and this is required by the standard. and they're accessed via fixed size offsets from the beginning. So pointers to any object are pointing to the beginning of the object always. So getting the A2 field from an A object, we'll just grab bytes 4 through 8 from the underlying representation. That's exactly what I just said. So let's say that this is an object in a hierarchy. Let's say the data members, or same thing as before, we have our data members for our base class, and the data members for any derived class are just tacked onto the end. It's that simple. So let's say we have int double, and then we have a b pointer and an int after that. They are just tacked on to the end of the existing object. Because this is a b object, remember b objects are also a objects, so we still have all the data from the a class, and we also have the b data. So important thing to note here, the a and the b pointers point to the start of the object. So when we say, you can use a child class pointer wherever a parent class pointer is expected, well, it's because they are pointing to the same location in memory. They both point to the start of the object. So, the value of the two pointers are the exact same. So you can use them interchangeably, or you can use child class pointers where parent ones are expected. You can't do the reverse. And getting the A2 field from an A or B object will still do the same thing. It'll just grab the relevant bytes. Okay, so virtual functions. This is where we're going to stray from EX280 a bit, because I seriously doubt they're talking about this. A virtual function, I know they talk about virtual functions, but there are 3 specific requirements that are needed in order for a function call to be considered a virtual function call. It needs to be made through a pointer to a base class. It doesn't need to be the base class, just a base class. It needs to be made to a function that is marked virtual in the base class, and it needs to be a function call that is not explicitly qualified. You can do things like explicitly call the parent class version of a function with like base : func name. But that's not what we're talking about here. We're talking about an unqualified name. And virtual function calls always call the most derived version of a function given the object's dynamic type, the calling object's dynamic type. And we'll touch on this more in a bit, but I think it's pretty intuitive for anybody that has worked with virtual functions before. Okay, so remembering those 3 rules, let's take a look at an example here and try to figure out what it prints together. So let's say this is main. Let's say we create a base object and a derived object. So nothing happens so far. Let's say we have a base pointer that is pointing to a derived object, and we have a derived pointer which is also pointing to a derived object, that same derived object. So let's say we do d.foo, and this is just the derived object itself, and we're calling .foo on it. Can somebody give me a guess? What is this going to do? Which version of the function is it going to call? That's okay. I can. Oh, derived foo. Totally right. You nailed it. Derived foo. And actually, let me just open up all the answers real quick here, and then we can work through them one by one. So derived foo. Also, when we do, I guess the main thing to note here is that this is not a virtual function call anyways, because we aren't doing it through a pointer. So this is just going to call D's version of foo, even if there were more derived classes underneath this derived class. And we'll see that at the end here. So when we call D pointer arrow foo, this is also not a virtual function call because D pointer is not pointing to a base class. References are polymorphic as well. Really? I'm pretty sure that's not the case. Oh, the references are just pointers with value semantics. Okay, I see. I would need to probably verify that myself, but at least if you're using an object itself, not a reference to an object, I know that that does not use, that does not have polymorphic behavior. But yeah, I guess that makes sense that references would do the same thing as pointers. Anyways, D pointer calling foo on D pointer. Remember, D pointer is just calling or it's just referring to the address of a derived object. This is going to call derived foo as well, because it's not to a base class. B pointer arrow foo, this is going to call derived foo because it is a virtual function call. It's made through a pointer to the base class. It's made to a function that is marked virtual, so virtual foo, and it's not explicitly calling the derived or base version, so it's going to make the most derived call based on the type of the object, which is a D. D.base : foo, so we're explicitly, even though this is a derived object, we're explicitly calling the base version, so we'll get the base version. D pointer arrow base foo, same thing, we'll get the base version if we ask for it. D.bar is going to call derived bar because we're calling it on a D object. B bar, same thing. And then D pointer arrow bar will call derived bar because it's the most, I guess these aren't marked virtual, so it's just going to call the version that you would expect. And same with B bar, it's going to call base bar because this is not marked virtual, so it's not a virtual function call. Question from the chat, do you need override in the derived class? No, you actually do not. The only thing that matters is that a base class version of the function is marked as virtual. If you put virtual in any of the successive classes or override, which is the like stylistically preferred way to do it, it is just considered good style. And it will allow the compiler to yell at you if you are clearly doing something wrong, which is always a good thing. You want to figure out your errors as soon as possible. So anyways, that's all good and fun. You guys probably already knew all that. But the question is, how does this actually work? How do virtual functions get implemented under the hood? And understanding this can help you navigate large hierarchies. So introducing this idea of a V table or the virtual function table. The big idea is that we can map classes to a table of virtual functions that they have in them. And for each class, we can keep track of what versions of the functions we should call if a virtual function happens. So thanks for that, actually. I will take a look at that link after. Anyways, for each object in the class hierarchy, we can remember, I guess, what the relevant table is, and remember if a virtual function is called on such an object, we know exactly which version of the function to call. And this pointer is initialized and like tracked behind the scenes, and you will never see it. And all this can be generated at compile time so that we still have like O of 1 function calls. Some other programming languages can't really get away with this. For instance, Python, when you are doing, I guess, dynamic function lookup, it is just doing a hash table access under the hood to basically check is the type of this object, or for the type of this object, you know, do a hash table index to see which version of the function should be called. And in C++, we can do it without a hash. It's just a pointer D reference. So anatomy of a V table. Data members for child classes are just put at the end of the object after all the parent class data members. And it's the same for a V table. So the V table for class A, we have two virtual functions. So we have two entries in our V table for class A. And for class A, if you ever have an A class object and you call foo on it, you're always going to want to call A's version of foo. Same for bar. You're always going to want to call A's version of bar because there is no other option. It's just an A object. For B, which inherits from A, V table for class B. For foo, we're going to call B's version of foo because there is a virtual function in the base class which is overridden by the derived class. And if we wanted to have good style, and I'm just being sneaky here, but if we wanted to have good style, we would do override, as somebody mentioned. So I'll put that in there for now. I think that's good to remind people to use that. So B's version of foo will be called if we have a B object and we have a virtual function called to foo. For bar, however, we are not overriding the base class version of bar, so we're going to get A's version of bar. And for Baz, we're going to get B's version of Baz because it doesn't even exist in A, so there's no other option. So with these, let's take a look at this, and we can see how they actually work. The V pointer is stored as the first data member and is hidden from users. So every time you have any object which has virtual functions either inherited or in the class itself. The first 8 bytes are actually going to be used for the v pointer, and it's pointing to one of the v tables for the hierarchy. So let's say we create an A object. During construction, the A constructor will be called, and it will set behind the scenes this v pointer to point to A's v table. And thus, if we ever call, so if this is an A object, it would point to the v table for class A. If we had a B object, it would point to the v table for class B, and of course we'd have our B data members. I guess that was it. But if you want to get into the nitty gritty, because of how construction and destruction happen in a hierarchy, basically this v pointer setting it happens while the object is being constructed. So for reasons associated with that, if you call virtual functions at any point while an object is being constructed, you get undefined behavior, which it normally behaves in the way you think it would, but it's undefined behavior technically. The implementation is free to set this v pointer how it wishes, and maybe it will wait longer than you'd expect it to set the v pointer to the right spot. Okay, anyways, vtable summary. This is the engine for polymorphic function calls in C++. Runtime overhead is just a pointer dereference and an array access, and it only happens when a virtual function call is made. And this is only generated at compile time whenever there is a virtual function in your class that you inherit. Cool. Variadic templates. These last two are super, super quick. So we're almost done here. Variadic templates. The basic idea is that variadic templates are functions that can take in any number of arguments. So the process by which you would use or define a variadic template is recursive. You basically process some constant number of arguments, and then you recurse with the remainder of the arguments. And this is how you must write variadic template code in C++. I'm not sure if it works differently in other programming languages. So in Python, there's a print function which can take in any number of arguments. And it's very similar to like the cout style printing in C++, but it just looks like a function call called print. And how it works, well, I guess we can implement something similar in C++. So what we do is we have two versions of this print function. We have our base case version, which only takes in one item, and it can be of any type, so long as it can be printed out. And we have our non-base case version, which takes in this t first parameter, and then this args ... type parameter pack. So this is a very specific syntax for variadic templates in C++. You need to do this type name ... args if you want to use a parameter pack. And in your parameter list itself, you need to do args ... and then the name of your parameter pack. So very, very weird stuff you've probably never seen before. This is yellow because it's really not that important to understand. I've used this once in 482 just for fun, basically, and to make my printing code and debugging code more easy. But what we would do in this case is we have our print function, and if this version of the function is called, we know that there is more than one argument specified, because if there was only one argument specified, the compiler would prefer this version. And it's going to print out the first thing with a space, and then recurse on the print function, unpacking the rest of the args, which is what that ... does. And eventually we will get down to this base case where only one argument's unpacked, and we will print our endl, and we'll be done. So in main, if we print A5, 1 + 2, and apple, we'll get A5, 3, apple. And because of templating and things like that, because the cout insertion operator already has definitions for each of these types, we can have our Python-like print function. Yep, and this base case code is very important. Code will not compile without it, because this final call right here will unwrap into a print with 0 arguments. And that does not match this definition here, and it does not match any definition of print. So we will get a compile time error. So yeah, you can do, if you wanted to, you could process more than 1 argument at a time. You could do a print pairs function, which takes in 2, and it processes 2 and then recurses on the remainder. Simple stuff. Well, a simple modification on the previous example. And like I mentioned before, errors will be thrown at compile time if there's ever no matching call. So let's say we call print pairs with 1, 2, 3, 4, 5 items. And 5, notably not divisible by 2. You can't print 5 in a sequence of pairs because the last one will not have a pair with it. So what's going to happen is the compiler is going to, during compile time, it'll like unwrap this code. It'll see a print pairs call with 5. It will generate a print pairs call with these first 2. It'll generate a print pairs call with these second 2 when we recurse. And then finally, it will generate a print pairs call with just 1 argument. And it will realize, wait, we don't have a function that only matches print pairs with 1 argument. So therefore, compile time error. Yep. And compiler detects this, throws error. Alrighty, we're almost done, everybody. Multiple return values in C++, structured bindings. This is just another fun one because it's not possible. So disappointing. You hate to see it. But we can come pretty close using a couple of C++'s other features. And maybe this is a thing since C++20, I don't know, but I have not updated these slides, so I can't tell you. Attempting multiple return values in C++. Before structured bindings, we would have to do something like pass in a pointer or a reference to a return value in the parameter list. So if you wanted to return an int and a string, you could pass in an int reference and a string reference to the function, and then, you know, set those values at some point during the function. You know, it's just kind of janky. You could return a struct which houses all the values. So, you know, some struct that has an int and a string as member variables, or you could return a std tuple which has all the values in it. Each of these are just not very clean, and you'll see with other programming languages like Go or Python that you can just return multiple things and accept them from a function call, from the return of a function call, and it's just very cool. Yeah, I was talking about C++ 17, or rather I was talking about if there are any new features in C++ 20 which make multiple return values possible. I'm not aware of them because I only updated these slides after C++ 17. Yeah, I'm not at all sure. Fold expressions, no idea what that even is. That's pretty neat though. Clearly have a lot of knowledge about this stuff. Okay, anyways, structured bindings. What they do is they take in a tuple-like object and they unpack it into separate variables. Let's just skip ahead to how to use it. So the anatomy here, type is usually auto. Usually auto reference actually. Then you do square brackets, name of variable, name of variable, name of variable until you've got all of the things you want to unpack, and you assign a tuple-like object into it. So here's a quick example. If you were to do, and this is a real world example that I think is super neat, the insert function in any of the map types in C++ returns to you an iterator and a Boolean. And the iterator is to the value, that you inserted. And the Boolean is whether or not the insertion succeeded. So you can do something like this: auto and then 2 names of new variables that are being initialized on this line equals myhash.insert. And the iterator, the, I guess, iter variable will now hold the iterator pointing to the hello object, and success will be true or false based on whether or not this worked. You can also do something like this where you create a time t, and time just has int in it, and you can do auto reference HMS equals t, and then you can set HM and S to set the fields of this time object. Pretty neat. You can also do something like, so you have a function that returns a tuple of int and string reference. You can do, you know, const auto reference number my stir to unpack the result of that foo call into a number and a stir. So yeah, neat stuff. Not super useful, but a nice quality of life feature. There are not many of those in C++, so we got to take what we can get. All right, so that is it from me. If anybody has any questions, feel free to shoot. It can be about anything, but honestly, at this point, you should just be happy you've made it to the end of EECS 281. I hope you are all enriched in some sense by the content that has been taught in this course, and I'm sure you will all do well in your future. Yeah, and I didn't actually update this slide, but let me do that real quick. Some other instructors had thoughts for future courses to take. Oh yeah, these are my recommendations, and other recommendations from students were from other staff members. That course. Why did I get such a weird spacing on that? Whatever. This course, I also highly recommend that course. This course I've heard good things about. Cool, stuff like that. Okay, this is the most, thank you. I don't know if I can really take credit for that. This was, to be honest, not my best work presenting this slide deck. I should have done a little bit more preparation, but either way, thank you guys for sticking around, and I hope you learned a thing or two. Please take this knowledge and dig more into these topics as you're interested. Why did they cancel 381? A great question. 381 was my favorite course I've ever taken, and they canceled it because the professor who ran the whole class retired. And the point of the class was basically to teach you about coding style and design patterns in advanced C++. And the professor hand graded everybody's projects because it was about style. You know, it wasn't exactly something that could only be auto graded, and the professor would himself go through and hand grade everybody's code with a red marker. So because of that, I think nobody really wanted to pick up that mantle because that's a lot of work for one professor to do. But either way, great course. The course website is actually still up. Yeah, and if you want, yeah, this was the semester I took it, actually, the very last one. I'll put this in the chat if you want to take a look at things like handouts. Let's see. He's got like, this professor was brilliant. He's got like the best write-ups for like using smart pointers, like such simple descriptive documentation for like using these complex features and stuff. And the projects are still all, the specs are all out there. So I don't know, feel free to take that course on your own if you really want to. 398 is now called 390. Yep, totally right on 381 why the prof retired. Yep, nobody wanted to hand grade that much. Totally true. Yeah, if 390, I highly recommend, if you're talking about if this is Amer's version of programming languages, I highly recommend that. It's phenomenal. Let's see what else. There's a group at MSU that meets and talks weekly about advanced C++. Seems like what 381 was. It's a 1-credit course, and that's where I learned much of what I know. That's really neat. Yeah, no, that's super cool. I wish there were more groups like that. Maybe there even are. I just am not aware of them. Anyways, that is going to do it for me. If you have any questions about anything, I'd be happy to stick around and answer them. But otherwise, I think